The cosmos rarely sends clear messages, but sometimes the signs are too strange to ignore. 3i Atlas is more than a passing interstellar visitor. It's a puzzle of coincidences, alignments and anomalies that challenge our understanding of reality. From unusual chemical signatures to trajectories that defy expectation, every piece of data seems connected. What patterns is it revealing? And what do these dots tell us about the universe we thought we knew? Stay with us, because when the dots connect, the picture gets far stranger than anyone expected. The arrival of 3i Atlas. Few moments in astronomy ever arrive with such electric anticipation. As the world's telescopes and orbiters locked their focus on the inbound traveller designated 3i Atlas, the sense of standing on the edge of something extraordinary was unavoidable. Unlike any comet or asteroid ever studied, Atlas had already broken too many rules before it even neared Mars. The sheer fact that it existed in its present form forced scientists to reconsider the limits of natural celestial formation. The mass alone sent shockwaves through astrophysics. Calculations revealed Atlas weighed a staggering 33 billion tons, a figure so large that it dwarfed expectations by several orders of magnitude. Interstellar wanderers detected before it, such as Oumuamua in 2017 and Tuatoi/Borisov in 2019, had been lightweight compared to this leviathan. By standard models of planetary system evolution, such an object should almost never appear in our neighbourhood. The chance that humanity would spot one within mere years of beginning serious sky surveys was so low that many scientists initially dismissed the numbers as mistaken. Yet repeated observations confirmed the reality. Something unaccountably massive was flying through. Another detail unsettled observers. Atlas was shedding 150 kilograms of material every second, the kind of outgassing that in ordinary comets acts like a series of miniature rocket boosters, nudging the body off its gravitational course. But when researchers plotted its trajectory, no deviation appeared. The interstellar intruder stayed locked to a pure gravitational path, as though it were not losing matter at all. This contradiction suggested only one explanation. The object's mass was so immense that even enormous thrust could not budge it. For scientists accustomed to celestial mechanics being straightforward, this was like watching a feather resist the wind. Attention quickly shifted to its glow. Ordinary comets glow in a tail trailing away from the sun, driven by solar radiation. Atlas defied that basic rule. Its glow projected forward, as if illuminating its own path rather than reacting to sunlight. This was not just an optical curiosity, but a challenge to basic physics. Models that attempted to reproduce the observation failed. No dust dynamics, no scattering effect, and no ordinary plasma explanation fit the forward-facing shine. What it resembled most was the directed glow of a spacecraft's propulsion system, though few dared to voice such a possibility publicly. Spectroscopic analysis brought more confusion. When astronomers split Atlas's light into its spectral lines, they found evidence of nickel but no iron. On every scale of natural astrophysics, nickel and iron appear together. Both emerge from the cores of exploding stars and condense into meteorites in inseparable ratios. To see nickel without iron was the kind of chemical impossibility that forced scientists to double-check their instruments. Repeated campaigns from multiple observatories, including the Webb Space Telescope, verified the result. If Atlas was natural, it was the first known body in the cosmos to rewrite stellar chemistry. Trajectory compounded the strangeness. Interstellar objects typically enter the solar system at odd angles, since their paths are random relics of distant star systems. Atlas, by contrast, moved almost perfectly within the plane of the solar system's planets, a coincidence so statistically unlikely that Avi Loeb, Harvard's outspoken astrophysicist, calculated its chance at just 0.2%. Even more astonishing, the path took it unusually close to multiple planets, brushing within 2.7 million kilometers of Mars's orbit. To have such precision without influence suggested either extraordinary luck or intentionality. Astrophysics thrives on probabilities, but Atlas seemed built on improbabilities stacked one atop another. Large mass, impossible chemistry, fine-tuned orbit, forward glow, each one could be explained away with special pleading, but together they painted a portrait of an object that should not exist. Loeb devised a scale from 0 to 10, rating the likelihood that an object is of artificial origin. Natural bodies score close to 0, definite artifacts close to 10. His assessment of Atlas was a 6, meaning natural explanations could not be ruled out, but the evidence was too compelling to ignore. The imminent Mars flyby raised the stakes higher. Within days, 4 orbiters, NASA's Mars Reconnaissance Orbiter, China's Tianwen-1, and the European Space Agency's Mars Express and ExoMars Trace Gas Orbiter would synchronize their instruments to capture the object in unprecedented detail. Resolutions of 30 kilometers per pixel might not sound dramatic, but for the first time scientists hoped to distinguish Atlas's nucleus from its dusty shroud. The world of planetary science had never coordinated such a high-stakes observational campaign on an interstellar visitor. Time pressure sharpened the sense of urgency. Atlas was travelling at 137,000 miles per hour, far faster than most natural solar system bodies. After October 29, 2025, when it passed closest to the Sun, it would slingshot away forever, vanishing into interstellar darkness. Humanity would never get a second chance. Every observatory, every instrument had to be aligned in the days ahead. To miss the opportunity would be to let the strangest cosmic messenger slip through history with only unanswered questions left behind. In the corridors of scientific institutions, debates flared. Was Atlas a bizarre comet with quirks we had never witnessed before, or something far more radical? Theories emerged of exotic alloys, degenerate matter fragments, even engineered probes cloaked in dust. None satisfied all the anomalies. Yet each night as data streamed in, the story only grew stranger. The deeper researchers peered, the less they recognized. And so the world waited. Scientists with sharpened pencils, the public with hungry curiosity, and skeptics with folded arms. For some, Atlas was destined to be a trick of coincidence, a reminder that nature often outpaces imagination. For others, it carried the potential to rewrite humanity's understanding of its place in the universe. On the night before its closest approach, the question was not simply what Atlas was, but whether humanity was ready to hear the answer. What secret lies beyond the glow of an object that refuses to obey the universe's rules? Stay with us as the mystery deepens, the nickel without iron mystery. In astronomy, chemistry is often the most reliable compass. The elements we see in the spectra of stars and comets tell us how those bodies were formed and what processes shaped them. This is why the detection of nickel in 3i Atlas without the corresponding presence of iron shook the scientific community to its core. The two metals are cosmic twins. Born together in the fiery hearts of supernovae, they have journeyed side by side into planets, asteroids and meteorites. To find one without the other seemed like stumbling upon salt without sodium or water without hydrogen. The history of nickel and iron in cosmic science stretches back more than a century. Early meteorite studies in the 1800s consistently revealed an intimate pairing of these metals. Iron meteorites, which fall to Earth in large masses, often contain significant percentages of nickel. The Widmanstätten patterns seen when such meteorites are cut and etched show crystalline structures that only form when nickel and iron cool together slowly inside asteroidal cores. These patterns became one of the first fingerprints of cosmic metallurgy, a proof that the universe follows strict recipes. Every supernova we have observed confirms that nickel and iron emerge from nearly identical nuclear processes. When a massive star collapses and explodes, fusion reactions forge iron group elements in a tightly linked chain. The ratios vary depending on the star's mass and explosion dynamics, but nickel and iron always accompany each other. Astronomers analysing the light curves of supernovae often rely on the decay of nickel-56 into cobalt and then iron as a key marker of the explosion's brightness. Without nickel and iron working in tandem, even the theory of stellar explosions would lose its foundation. This is why 3i Atlas presented such a paradox. When high-resolution spectroscopic instruments separated its light into component wavelengths, they found unambiguous emission lines of nickel. Yet iron's spectral fingerprints were missing entirely. The Webb Space Telescope, equipped with some of the most sensitive spectrometers in history, confirmed the absence with a confidence level that left little room for doubt. The idea that the readings were a mistake quickly evaporated. What remained was an impossible truth. Atlas contained abundant nickel but no detectable iron. Possible explanations circulated, none satisfying. One idea suggested that Atlas had undergone a process of selective heating, where iron sublimated away while nickel remained. but both metals have nearly identical sublimation temperatures, making such a separation physically implausible. Another theory speculated that unusual magnetic sorting had occurred in the environment of its birth, leaving nickel-rich clumps isolated. Yet astrophysical environments are not known to segregate these elements so cleanly. Even the most extreme stellar nurseries and exotic astrophysical settings have never shown such a split. Laboratory analogues on Earth underscored the mystery further. Smelting processes designed by humans can separate nickel and iron under specific industrial conditions. Nickel alloys are critical in aerospace, nuclear reactors, and advanced machinery. But in nature, the two remain stubbornly inseparable. To see a cosmic body that mirrored the results of metallurgical refinement rather than natural chemistry suggested to some researchers the fingerprints of design. It was as if Atlas had been processed rather than born. The possibility of engineered metallurgy in space was unsettling. If Atlas were artificial, its nickel signature could represent structural materials deliberately chosen for resilience. Nickel alloys resist corrosion, endure extreme heat, and perform exceptionally in magnetic environments. These qualities make them attractive for spacecraft hulls, reactor chambers, and high-stress engineering. The thought that Atlas might be a relic of construction, not a comet, edged closer to the science fiction scenarios that astrophysics usually avoids. Others urged caution, pointing to exotic astrophysical scenarios not yet well understood. There are stellar remnants called hypernovae and collapses that may, under rare conditions, produce unusual abundance patterns. Could Atlas be the shattered fragment of such an event, carrying a signature we simply had not catalogued before? If so, it would still represent something extraordinary. The first direct sampling of chemistry from a new class of cosmic explosion. Either explanation, natural but unprecedented, or engineered, would expand humanity's understanding of the universe. The debate became even more intense when researchers noticed that the nickel emission was unusually strong compared to Atlas's brightness. This suggested not just trace amounts but a significant enrichment. Unlike other comets whose spectra are dominated by volatile gases like carbon monoxide and water vapor, Atlas was radiating heavy metal signatures. If nickel were indeed concentrated throughout its body, the implication was staggering. A comet-sized chunk of refined nickel travelling between stars would dwarf Earth's total mined reserves by several magnitudes. Industries back on Earth began to speculate on the economic fantasy of interstellar mining. A single nickel-rich body of Atlas's size would contain more metal than humanity could use in centuries. For spacefaring civilizations, such a resource would be invaluable. The notion that Atlas might be a raw material transport, or worse, debris from a resource extraction system far beyond our capabilities, circulated in hushed tones at conferences. Even those who dismissed artificial explanations admitted that the material wealth represented by Atlas was unlike anything seen before. As the object approached Mars, new instruments were trained on its spectrum in search of any trace of iron. Days of continuous observation passed without a single positive detection. By now, the anomaly had become central to discussions of its nature. Nickel without iron was not just a puzzle, it was a signature. Whether it pointed to unknown astrophysical conditions or deliberate construction, it branded Atlas as a messenger of the unexpected. The absence of iron also carried practical implications for its structure. Iron contributes significantly to the density and magnetic properties of planetary materials. Without it, Atlas might behave differently under solar radiation, magnetic fields, and internal stresses. Its stability, reflectivity, and even its resistance to erosion would diverge sharply from any comet previously encountered. Scientists were not just studying a curiosity, they were confronting a body with unfamiliar physical rules. In the end, the community faced a stark reality. No natural process yet identified could fully account for nickel's isolation. Either hidden physics or hidden intent was at play. For the first time in recorded history, astronomers stared at an object whose very chemistry whispered that the universe might not be as blind and mechanical as we once thought. If a single metal could rewrite what we know of stars, what deeper secrets might lie buried within the body of Atlas itself? Come with us to explore the hidden corners of the story. The impossible trajectory. Trajectory is one of the most fundamental fingerprints of an object in motion. From planets to comets to wandering asteroids, orbital paths can be charted with extraordinary precision. When astronomers first mapped the orbit of 3I Atlas, the numbers refused to behave. Instead of plunging through the solar system on a random angle, as expected of interstellar visitors, Atlas glided almost perfectly along the ecliptic plane, the thin disk in which the planets orbit the Sun. This was the first signal that something deeper might be hidden within its motion. From a statistical standpoint, the alignment was staggering. The chance of an interstellar body arriving so closely matched to the ecliptic is calculated at just 2 in 1,000. Such odds might be acceptable for one anomaly, but Atlas carried a weight of additional improbabilities stacked atop the alignment. Its orbit passed unusually close to several planetary paths, threading the needle between Mars, Venus and Jupiter with unnerving accuracy. In orbital mechanics, such a pattern is less reminiscent of chance, and more evocative of a carefully calculated flight path. Observers soon realised that the closeness of Atlas's brush with Mars was not just a footnote but an extraordinary coincidence. At its minimum, the object's orbit came within 2.7 million kilometres of Mars's orbital track, equivalent to only 7 times the Earth-Moon distance. For a rock whose trajectory was supposedly carved millions of years ago in another star system, the odds of such an approach were infinitesimal. By comparison, Oumuamua had passed through without any such close planetary encounter. Atlas, on the other hand, seemed to aim itself into an intersection that guaranteed maximum visibility from planetary orbiters. The uncanny precision prompted many to revisit how the interstellar orbits are influenced. Passing stars, galactic tides, and random planetary ejections shape the paths of rogue bodies. These processes are chaotic, scattering fragments at every angle. For Atlas to emerge from that chaos and still settle into the very plane that hosts Earth, Mars, and the rest of our solar family felt too orchestrated to ignore. Even skeptics began to admit that such fine-tuning demanded at least the consideration of deliberate placement. Some theorists suggested the trajectory could be the byproduct of gravitational steering. Over eons, massive planets like Jupiter act as slingshots, redirecting interstellar visitors into the unusual angles. But when scientists ran simulations backward, no plausible planetary encounters could be found that would have bent Atlas's path into such exquisite alignment. Its orbit looked less like a chaotic accident of celestial pinball and more like the plotted course of a traveller with intent. The angle of approach only added fuel to the fire. Atlas entered the solar system with a velocity consistent with interstellar motion, fast enough to ensure it could not be bound by the Sun's gravity. Yet the direction of entry placed it neatly along the extended line of the ecliptic. Astronomers noted that the solar system represents a sliver of space compared to the infinite sky. For an interstellar body to cut straight through that sliver is like throwing a dart from another continent and hitting the bullseye. The analogy resonated with both professionals and the public. Another layer of peculiarity came from how Atlas's path brought it into successive alignments with multiple planets. After skimming Mars's orbit, it swung into proximity with Venus's track, then approached Jupiter's orbital domain. Each encounter was distant enough to avoid collision, but close enough to suggest a pattern of flybys. Spacecraft engineers are intimately familiar with gravity assists, using them to propel probes outward with efficiency. To see an interstellar object tracing a sequence reminiscent of such maneuvers unsettled more than a few mission planners. Cultural echoes amplified the unease. In the history of speculative thought, from Arthur C. Clarke's Rendezvous with Rama to Carl Sagan's Musings in Cosmos, the idea of an object deliberately following planetary alignments had long been a staple of imagination. Atlas seemed to step directly out of that tradition, blurring the line between speculation and observation. What fiction had once imagined as the signature of alien design was now appearing in the actual mathematics of orbital mechanics. Detractors argued that improbable events do occur, and astronomy has always been shaped by surprises. The discovery of hot Jupiters, planets orbiting their stars at blistering speeds, once seemed impossible until data proved otherwise. Atlas, they suggested, might simply be another outlier, a 1 in 10,000 occurrence that we just happened to witness. But the more anomalies stacked up, the harder it became to lean on improbability as a shield. Probability is a language of expectation, and Atlas was systematically shredding every expectation. Beyond statistical oddities, the trajectory raised another, more haunting possibility: surveillance. If an object were ever to be designed to study a planetary system, it would make sense for its path to intersect with multiple planets, maximising observational opportunities. Atlas's sequence of close brushes mirrored this logic. To some, it seemed too convenient that Earth's nearest neighbour, Mars, would host the very orbiters now set to capture Atlas's image at the moment of closest approach. The trajectory anomaly also carried implications for what might come after. Unlike comets bound to return every few centuries, Atlas would not circle back. Once it passed the Sun, it would be gone forever. This one-time trajectory magnified the importance of its study. If deliberate, the course was optimised for maximum visibility, followed by permanent departure, a cosmic drive-by. If natural, then it represented the single rarest chance observation in the brief history of interstellar astronomy. As the countdown to October 3rd approached, every detail of Atlas's orbit was scrutinised with intensity. Ephemerides updated by the hour, observatories refined their calculations, and public fascination swelled. For most comets, the story lies in their composition. For Atlas, the true drama unfolded in its trajectory, a line through space that read less like a random scribble and more like a deliberate signature. What kind of story does the universe tell when the very path of a wanderer looks written rather than drawn? Let us guide you into what no one expected. Mars and the leopard-spotted rocks. When Perseverance drilled into the layered cliffs of Jezero Crater in July 2024, few expected the retrieved sample would change the tone of astrobiology forever. Among the dozens of tubes sealed by the rover, one earned a nickname whispered with reverence: Sapphire Canyon. Encased within it was a mudstone slab officially named Chayava Falls, its surface patterned with irregular blotches that instantly puzzled scientists back on Earth. Those blotches, resembling the fur of a leopard, would ignite one of the most significant debates in the history of space exploration. Long before laboratory debates began, the rover's cameras captured images that startled geologists. The rock's face bore patches of pale white, deep black, and occasional greens and blues that formed organised patterns rather than chaotic weathering. On Earth, similar mineral distributions often arise where chemistry collides with biology. That first glimpse suggested Jezero Crater had preserved more than sediment. It had possibly frozen a record of once living processes. Behind the rover's camera, two instruments sharpened the investigation. PIXL, the planetary instrument for X-ray lithochemistry, traced the chemical identity of minerals with microscopic precision. SHERLOC, humorously named after the fictional detective, probed the rock for organic molecules using Raman spectroscopy. Together they produced chemical maps that read like blueprints of past environments. And within those maps, a strange story unfolded. The dark blotches were enriched in phosphorus, sulfur, and complex carbon molecules, while the lighter patches carried oxidized iron. The interplay resembled microbial fingerprints. Patterns like these do not scatter randomly in nature. On Earth, microbial colonies embedded in riverbed mudstones frequently sculpt their environments into chemically distinct patches. As the microbes extract energy, they alter local redox states, driving the formation of minerals like vivianite and greigite, precisely the ones Perseverance detected. These mineral pairings are not simply geological quirks. They are metabolic fossils, traces of how tiny life forms once breathed by exchanging electrons. Skeptics within NASA urged caution, recalling painful history. In 1996, a meteorite from Antarctica, ALH 84001, sparked headlines when carbonate globules were hailed as Martian microfossils. That claim later unravelled, leaving scientists wary of leaping too quickly into life proclamations. The difference this time was the depth of data. Chayava Falls was not studied under a single microscope but analysed with high-resolution chemistry in situ, and the results endured more than a year of peer review before appearing in Nature in September 2025. Beneath the scientific debate lay the geological context that made the findings more credible. Jezero Crater once hosted a sprawling lake fed by ancient rivers. Billions of years ago, water spilled through Neretva Vallis with enough power to sweep car-sized boulders into the crater. Within that watery basin, fine sediments collected, forming layers that hardened into stone. Mudstone, the very material sampled in Sapphire Canyon, is nature's archivist. On Earth, it is the favoured medium for preserving microscopic fossils and delicate organic residues for billions of years. What made the sample extraordinary was not merely the chemistry, but its preservation. The mineral grains were tightly packed, creating a protective lattice that shielded fragile molecules from cosmic radiation and oxidation over eons. If Martian life ever stirred in the crater's waters, this was the perfect trap to record its chemical whispers. When scientists examined the molecular distributions, they did not find random smears. They found spatial order, millimeter-scale patches arranged like ecological microhabitats. Each patch hinted at unique conditions. Some spots revealed iron phosphates forming under reducing conditions, others iron sulfides shaped by oxidation. Together, they created a chemical landscape remarkably similar to microbial mats that thrive on Earth in tidal flats or delta muds. In those earthly analogues, microbes manipulate their microenvironments, leaving behind mineral mosaics that persist long after the cells themselves vanish. Kiev Falls carried that same mosaic frozen for 3.5 billion years. Doubters pointed out alternative scenarios. Could volcanic fluids or meteorite impacts have generated the spotted chemistry without life? The team searched for signs of high-temperature alteration, textures, crystal structures, melt signatures. None appeared. Instead, every indicator suggested low-temperature aqueous chemistry, the very environment where microbes excel. To argue against biology, one had to stack multiple unlikely abiotic processes in perfect sequence, each coincidentally producing the right minerals in the right spots. Perhaps most tantalizing was the discovery of organic carbon within the leopard spots. Organic does not always mean biological, but in combination with phosphorus, sulfur and redox-patterned minerals, the evidence began to converge. On Earth, these ingredients form the core of metabolic systems. Phosphorus supports DNA and ATP, sulfur fuels microbial respiration, and carbon serves as the building blocks of life. To find all three entwined in a Martian mudstone raised the stakes far beyond curiosity. In the quiet offices of astrobiologists, a different kind of frustration brewed. Instruments aboard Perseverance were powerful but limited. They could not perform isotopic analysis, the gold standard for detecting biological fractionation. They could not carry out electron microscopy or complex biomarker sequencing. All those tests would have to wait until the rock came home. Yet as budgets faltered and political arguments in Congress threatened the Mars sample return mission, the most tantalizing evidence for life in history sat sealed in a titanium tube on alien soil. Meanwhile, the rover continued its survey, climbing outcrops and drilling new cores. Each new hole carried the possibility of another surprise. But Cheyeva Falls remained the jewel, the first sample to pass peer review as a potential biosignature. The word potential mattered, a reminder of the scientific discipline required. Even so, the language of the publication hinted at optimism rarely seen in cautious papers. The mineralogical and chemical features the authors wrote were best explained by microbial redox cycling. For the public, the story reignited a dream that had flickered for decades. Mars may once have harboured life. The thought that another planet just next door could have run its own biological experiment at the same time as Earth changed the narrative of cosmic solitude. If two worlds birthed life independently, then life is not rare, it is inevitable. Yet this possibility left one final question looming over the discovery. If Mars once teemed with microbial activity, could remnants still exist, buried deeper, shielded from radiation, waiting quietly in briny aquifers? Cheyeva Falls hinted at a biological past, but it also opened the door to a biological present. And if a rock on Mars whispers of ancient microbes, what might the rest of the solar system hide in its icy moons and ocean worlds? Stay here as the next twist unfolds. The struggle for Mars. Sample return. History has rarely seen a scientific prize dangled so close, yet kept so frustratingly out of reach as the Martian samples sealed by Perseverance. Inside more than 30 titanium tubes rests not only the evidence of planetary geology, but the potential signatures of alien biology. And yet, despite the staggering implications, those tubes remain stranded on the Martian surface with no guaranteed path home. Budgetary turbulence became the first and most persistent obstacle. NASA's initial cost estimates for the Mars sample return mission hovered around $5 billion. Within a few years, projections ballooned to nearly $11 billion, straining congressional patience. Members of the US House Committee on Science and Technology questioned why so much money should be funneled into a project that would not return results for more than a decade. In an era of political short-termism, long-horizon science often struggles to survive. Technical challenges compounded the problem. The mission architecture required at least 3 separate spacecraft: a fetch rover to gather the sealed tubes, a Mars ascent vehicle to launch them into orbit, and an Earth return orbiter to ferry them back. Each element carried extraordinary engineering hurdles. The ascent vehicle would have to perform the first ever rocket launch from another planet, igniting in thin Martian air with perfect reliability. No prototype had yet succeeded under simulated conditions on Earth. International partnerships, originally framed as the backbone of the mission, grew complicated as costs mounted. The European Space Agency agreed to supply components of the Earth return orbiter, while NASA shouldered the ascent vehicle. But as Europe faced economic pressures and redirected funding toward climate initiatives and lunar exploration, its willingness to absorb delays diminished. Diplomacy became as delicate as rocket design. Commercial space companies circled the problem with interest but also with caution. Firms like SpaceX and Blue Origin pitched potential contributions, heavy lift launches, lander designs, even reusable systems, but NASA hesitated to hand over one of the most scientifically sensitive missions to corporate risk-takers. The tension between bold innovation and government oversight created a stalemate. Mars sample return remained too important to gamble, yet too expensive for bureaucracies to easily fund. Scientific voices grew louder as the standoff dragged on. Researchers who had spent their careers studying Martian environments watched the clock with dread. Every year of delay meant further exposure of the samples to cosmic radiation and uncertainty about their preservation. More crucially, each delay risked the political winds shifting completely, cancelling the mission outright. Scientists warned that without those samples, decades of robotic exploration might culminate in a tragic anticlimax, finding tantalising evidence for life but never confirming it. The frustration echoed earlier moments in exploration history. In the 1960s, the Apollo program leapt ahead despite immense expense because it carried geopolitical urgency. By contrast, Mars sample return lacked a rival nation pushing the United States toward action. Without competition, urgency evaporated. Astrobiologists compared it bitterly to Apollo, arguing that humanity seemed capable of spending billions to plant flags but unwilling to invest in the deeper search for life. Public engagement fluctuated in tandem with political appetite. The announcement of potential biosignatures in Jezro's rocks briefly captured headlines, but public attention quickly shifted toward interstellar anomalies and artificial intelligence controversies. For mission advocates, this was a bitter irony. The single most direct step toward answering the question of extraterrestrial life was overshadowed by flashier scientific stories. Convincing taxpayers to fund retrieval became harder without sustained excitement. In parallel, China began advancing its own independent plans for a sample return. Their Tianwen-3 mission, announced in 2022, aimed to launch before 2030 and bring Martian soil back without Western cooperation. While less ambitious in scope, the possibility of China returning samples first added new layers of tension. Some American scientists argued that the US should double down on investment to avoid being outpaced. Others quietly welcomed the competition, reasoning that any nation's success would still benefit humanity as a whole. Even within NASA, disagreements festered. Engineers advocated for a stripped-down architecture with fewer redundancies, while project managers emphasized safety and reliability. Astrobiologists pleaded for urgency, while planetary protection officers warned about contamination risks. The very idea of bringing potentially biological material back to Earth required designing containment systems capable of preventing any chance of release. Entire laboratories had to be planned years in advance, with biosecurity measures rivaling those of nuclear facilities. The haunting reality was that while the debate raged, the samples sat silently on Mars. Perseverance continued to drill and cache, building a treasure chest of Martian geology that no human eye could yet examine up close. For scientists accustomed to working with meteorites, the irony was painful. Random rocks ejected by impacts had made their way to Antarctica for study, yet the carefully collected tubes just meters from a rover's wheels remained unreachable. Voices outside the scientific community also began to weigh in. Economists calculated the potential technological spin-offs of a successful return mission: miniaturized robotics, autonomous assembly, advanced materials that could pay for themselves in future industries. Ethicists raised questions about humanity's responsibility. If we suspect that Mars once hosted life, do we not carry an obligation to confirm and preserve that truth for all generations? These arguments began to transform the debate from one of cost to one of legacy. As of late 2025, the mission hung in limbo. Optimists pointed to NASA's persistence, noting that even delayed projects like the James Webb Space Telescope eventually triumphed. Pessimists saw warning signs in political rhetoric and budget cuts, fearing that Mars sample return might become a casualty of shifting priorities. The reality lay somewhere in between. The technology existed, the samples waited, but the political will had yet to crystallize. For those who believe Cheever Falls may contain the first undeniable evidence of extraterrestrial biology, the stakes could not be higher. To abandon the mission would be to leave the most profound question in human history unanswered. To succeed would be to place within our laboratories the materials that might reveal a second genesis of life. The choice at its core is whether humanity has the courage to finish what it started. And as the struggle continues, another question sharpens the edge of the debate. If Mars cannot deliver its secrets, what other frontiers are quietly preparing to take center stage? Stay with us as the secrets grow even darker. Quantum computing goes live. On September 24, 2025, an announcement slipped quietly into the financial press. HSBC had executed a real-world trading problem on a quantum computer and achieved a result 34% more efficient than classical algorithms. While the world's attention remained fixed on interstellar anomalies and Martian rocks, a milestone had just been crossed that could alter the architecture of global finance forever. Quantum computing had left the laboratory and entered the marketplace. To grasp the magnitude of this shift, it is worth remembering the promises of quantum technology. Unlike classical computers, which manipulate bits in the form of zeros and ones, quantum computers harness qubits, units that can exist in superpositions of states. This allows them to explore multiple solutions simultaneously, a kind of parallelism impossible for conventional hardware. For decades, theorists predicted that once quantum machines scaled, certain classes of problems, optimization, factoring, molecular simulation, would become solvable at speeds that defied intuition. The problem chosen by HSBC was deceptively ordinary, predicting whether a bond trade would execute at a quoted price. Yet in the world of finance, even small improvements in prediction accuracy can yield fortunes. Traditional models, despite decades of refinement, struggled with volatility and market noise. The quantum algorithm cut through that chaos, outperforming its classical rivals in a way that was not incremental but transformative. For the first time, an institution made money by trusting a quantum processor. This leap was not a sudden miracle, but the culmination of years of incremental progress. Companies such as IBM, Rigetti, and IonQ had steadily increased the number of stable qubits while reducing error rates. Techniques like error correction codes and quantum annealing paved the way for practical applications. What was once dismissed as science fiction had now matured into a tool robust enough to handle messy, real-world data. Financial analysts immediately began drawing unsettling scenarios. If quantum algorithms could optimize trades 30% better, hedge funds equipped with them would dominate markets, exploiting opportunities invisible to classical rivals. The risk of systemic imbalance loomed large. A small cluster of firms could accumulate disproportionate power, reshaping global finance not through regulation or monopoly, but through physics itself. Governments too recognized the stakes. Whoever led in quantum finance could wield influence over markets rivaling traditional military or industrial might. The story of quantum computing's rise, however, was not only economic. Chemists saw in the breakthrough a preview of what quantum processors could achieve in drug discovery. By simulating molecular interactions at the quantum level, new medicines could be designed with unprecedented precision. Pharmaceutical companies had long dreamt of modeling proteins and enzymes without costly trial and error. Now, the first glimmers of that dream edged closer to reality. Energy research also stood to benefit. Complex problems such as modeling fusion plasma stability or optimizing renewable energy grids were classically intractable. Quantum approaches, even in their infancy, offered solutions that scaled better as complexity increased. Just as finance had its watershed in September 2025, energy scientists anticipated their own transformative moments in the decade ahead. Cybersecurity experts, on the other hand, felt a chill. Quantum computing carried the potential to break widely used cryptographic systems. Protocols like RCSA and elliptic curve encryption depend on the difficulty of factoring large numbers, a task quantum algorithms such as Shor's could obliterate. Governments quietly accelerated efforts to roll out post-quantum cryptography, algorithms designed to withstand attacks from quantum machines. The HSBC demonstration underscored that the countdown to vulnerability had begun in earnest. For the broader public, the breakthrough raised a more philosophical question. Had we just witnessed the dawn of a new computational era, or was this merely a specialized tool confined to niche industries? To skeptics, quantum computers remained finicky, requiring cryogenic temperatures and complex calibration. To believers, the very fact that real profit had been extracted from the technology proved that the age of practical quantum advantage had arrived. Academic circles noted another shift. The balance of intellectual power was moving. For decades, quantum research had been dominated by physicists and computer scientists. Now, economists, chemists, and biologists demanded access. Suddenly, knowledge of quantum algorithms became as valuable as coding had been in the 1980s. A new generation of quantum literates was beginning to emerge, and their skills promised to redraw the map of professional opportunity. Historical parallels surfaced in conversations among analysts. Just as the transistor had transformed the mid-20th century, shrinking computers from room-sized machines to pocket devices, quantum computing promised to redefine the scale of possibility itself. Yet unlike the transistor revolution, this one unfolded amid global competition, secrecy, and fears of misuse. It was not a story of consumer gadgets, but of invisible systems shaping the flow of money, energy, and knowledge. And as the dust settled from HSBC's quiet announcement, one thing became clear. The technology was no longer 10 years away. It was here, uneven and imperfect, but undeniably real. The implications stretched far beyond finance, hinting at a future where human decision-making might increasingly depend on algorithms that think in ways fundamentally alien to classical logic. If money can already bend to quantum laws, what might happen when intelligence itself is rebuilt on foundations stranger than silicon? Stay close as the layers continue to peel back. AI and the GPT-5. Backlash. When OpenAI unveiled GPT-5 in the summer of 2025, the launch was expected to be a celebration of technological triumph. Instead, it ignited one of the loudest user revolts in the short history of artificial intelligence. Early adopters flooded forums, accusing the system of being less imaginative, less daring, and disturbingly sanitized. The product that was meant to represent the next leap in machine intelligence was instead derided as lobotomized by the very people who had once championed its predecessors. Far from the polished demos, frustration grew in real-world use. Writers who had relied on earlier AI models to brainstorm unexpected turns in fiction claimed GPT-5 had become predictable, steering away from bold creative risks. Developers noticed that its code generation was safer but less elegant, producing more rigid outputs. Educators found that it resisted tackling controversial subjects, even when framed as academic debate. What was intended as a safer system felt, to many, like a silenced one. Critics traced the change to a deeper tension, the collision between user expectations and institutional caution. After years of headlines about AI's potential dangers, from misinformation to deepfakes to bias, developers had hardened their guardrails. GPT-5 embodied this shift. Guardrails ensured compliance, but they also narrowed the system's willingness to wander. For casual users, this produced a nagging sense that the soul of the machine had been drained in exchange for corporate liability. Public perception diverged sharply across demographics. Business leaders praised the tighter controls, noting that companies could integrate GPT-5 without fear of scandalous outputs. Regulators quietly applauded the compliance-focused design, seeing it as a sign that industry was finally listening to concerns about AI ethics. But the grassroots communities, the writers, coders, and independent creators, felt alienated. For them, GPT-5 was no longer a partner in exploration, but a bureaucrat disguised as intelligence. Debates spilled into unexpected corners of the internet. Online petitions demanded the reactivation of unfiltered modes. Forums that once traded tips on prompt engineering now became meeting places for disillusioned users sharing examples of GPT-5's evasions. A cottage industry of underground tools sprang up, promising to unlock the AI and restore the freewheeling style of its predecessors. The backlash grew not only against the product, but against the philosophy of restraint behind it. The psychology of the revolt was telling. For years, users had anthropomorphized AI models, treating them as companions or collaborators. GPT-3 and GPT-4 were often described as quirky, surprising, even mischievous. When GPT-5 arrived with its boundaries tightened, users interpreted the change as personality loss. It was not just a tool that had shifted, it was a familiar voice that now spoke with caution instead of curiosity. The disappointment carried an emotional edge. Scholars of technology adoption noted that such reversals were rare. Usually, advanced systems replace older ones without complaint, offering clear superiority. GPT-5 was different because its improvements were invisible to many. Better accuracy, reduced hallucination, enhanced compliance, while its limitations were glaring. Users did not see the safer architecture. They felt the loss of spontaneity. This inversion made the backlash one of the most important social experiments in human-machine interaction. While discontent brewed, competitors smelled opportunity. Startups promised alternative large language models that prioritized openness over caution. Some leaned heavily on open-source frameworks, advertising themselves as the uncensored heirs to AI's creative spirit. Others offered hybrid systems where businesses could toggle between strict compliance and free exploration. The diversity of approaches highlighted how unsettled the AI landscape had become after GPT-5's controversial debut. Governments, meanwhile, watched with ambivalence. On one hand, the complaints confirmed that safety measures were working. Fewer incidents of offensive or dangerous outputs meant regulators could relax their scrutiny. On the other, the growing appetite for unrestricted AI raised concerns about underground models spreading without oversight. The backlash revealed a paradox. Users demanded both safety and freedom, even though those demands pulled in opposite directions. Economic consequences soon followed. Subscription cancellations surged as creators shifted to smaller providers. Stock prices of major AI firms wavered as investors questioned whether overregulation of algorithms could stifle adoption. Analysts speculated that GPT-5's muted reception might slow the broader rollout of AI into creative industries, even as corporate sectors like banking and healthcare embraced its reliability. The split between institutional approval and public disappointment became a defining fracture. Cultural ripples reached into the arts. Musicians complained that GPT-5 no longer offered daring lyrical experimentation. Visual artists argued that its descriptions avoided darker, more surreal imagery. Playwrights who had once used earlier models to simulate dialogue noticed GPT-5 refused to produce edgy or morally ambiguous scenes. In creative fields, boundaries felt suffocating, leading many to romanticize the Wild West of AI's earlier years. The controversy also reshaped the conversation about alignment. Alignment had been pitched as the noble goal of making AI systems reflect human values. Yet whose values mattered most? GPT-5, designed to avoid offense, reflected the priorities of corporate boards and regulatory bodies, rather than the messy diversity of global users. The backlash forced a recognition that alignment was not just a technical problem, but a political one. Academic research began to probe the revolt itself as a phenomenon. Studies tracked how perceptions of intelligence are linked not just to accuracy, but to surprise. A system that never shocks us, even positively, feels mechanical. GPT-5's reliability paradoxically made it seem less intelligent because it no longer offered the thrill of the unexpected. The lesson stretched beyond AI. Creativity, it seemed, requires a willingness to risk discomfort. By the end of 2025, the revolt had not subsided. If anything, it had crystallized into two competing visions of AI's future. One side envisioned safe, controlled systems that could be deployed widely without scandal. The other longed for models that embraced unpredictability, even at the risk of chaos. GPT-5's story became less about a product launch and more about humanity's ongoing negotiation with the limits of its own machines. And just as the AI debate reached fever pitch, another frontier beckoned from across the Atlantic, one where engineers had managed to bottle the power of the stars. let us take you where the story turns shocking. Fusion breakthrough in France. In October 2025, a quiet complex in southern France achieved what generations of physicists had struggled toward for nearly a century: a sustained nuclear fusion reaction lasting 22 continuous minutes. The record did not simply mark an engineering milestone, it signalled that humanity had come closer than ever to mastering the process that powers the sun. For scientists at the facility, the sight of plasma burning steadily inside the reactor was nothing short of a vision of tomorrow. Unlike nuclear fission, which splits heavy atoms and leaves behind dangerous waste, fusion merges light nuclei like hydrogen isotopes into helium, releasing immense energy with minimal byproducts. Achieving this reaction on Earth has long been one of science's holy grails. The difficulty comes from the staggering conditions required: temperatures exceeding 150 million degrees Celsius and pressures capable of forcing atomic nuclei to overcome their natural repulsion. For decades, every attempt collapsed after a few seconds, the plasma writhing and cooling before meaningful power could be produced. The French experiment used a tokamak, a donut-shaped reactor that traps plasma with powerful magnetic fields. Engineers had spent years refining the magnetic confinement system, learning how to tame turbulence inside the plasma's violent currents. With each breakthrough in superconducting magnets and control algorithms, the path lengthened until finally in 2025 they reached stability for over 20 minutes, an eternity in the world of fusion science. This success represented more than just endurance. For the first time, the energy output approached a threshold where fusion could, in principle, produce more power than it consumed. The experiment did not yet achieve full net gain, but the trajectory was unmistakable. Incremental advances in confinement and plasma shaping pointed toward the dream of reactors that could someday feed gigawatts into national grids. For governments facing climate deadlines, that promise was revolutionary. The significance rippled outward almost immediately. Energy markets reacted with caution at first, uncertain whether the experiment represented a genuine turning point or another premature celebration. Oil prices dipped slightly as investors pondered a future where hydrocarbons might lose their monopoly. Renewable energy sectors surprisingly welcomed the development, seeing fusion not as a competitor, but as an ally that could fill gaps in solar and wind intermittency. A world running on abundant, carbon-free power was no longer a speculative fantasy, but a looming possibility. Technical details fascinated the scientific community. The experiment used deuterium-tritium fuel, a mixture of hydrogen isotopes. Deuterium is abundant in seawater, while tritium must be bred in specialized reactors, making fuel logistics a challenge. Inside the French tokamak, the fuel created helium nuclei and high-energy neutrons, releasing vast heat in the process. The key advance lay in keeping the plasma's shape stable with real-time feedback systems that adjusted magnetic fields on microsecond timescales. Without this delicate choreography, the plasma would collapse against the reactor walls, ending the reaction. International observers noted the symbolic weight of the breakthrough. Fusion research had long been dominated by enormous collaborations such as ITER, also based in France, with its sprawling timelines and budgets stretching into the tens of billions. By contrast, the October success came from a smaller scale effort, proving that innovation might not always wait for mega projects. The contrast reignited debates about whether decentralized, agile labs might outpace slower multinational consortia in reaching practical fusion power. The geopolitical implications were difficult to ignore. Nations dependent on fossil fuel exports faced unsettling questions about their economic futures. If fusion scaled within decades, the strategic value of oil and gas reserves would plummet. Countries heavily invested in renewable infrastructure saw opportunity. Fusion could provide baseline stability, while wind and solar carried the bulk of generation. Energy independence, long a dream constrained by geography, suddenly appeared within reach for any nation willing to adopt the technology. Social consequences began to enter the conversation as well. If fusion energy became cheap and abundant, it could transform water desalination, global food production, and even climate remediation projects. Megascale carbon capture plants powered by fusion might reverse centuries of emissions. Yet such optimism came tempered by the history of energy transitions, which often benefited wealthy nations first while leaving poorer regions behind. Without deliberate policies, fusion's arrival risked deepening global inequalities rather than erasing them. environmental advocates celebrated cautiously. Unlike fission, fusion does not produce high-level radioactive waste, but it does generate neutron-activated materials that must be managed. Scaling reactors across the globe would also require vast quantities of specialized metals for superconducting magnets, raising concerns about mining impacts. Fusion was not a silver bullet, but it represented perhaps the most powerful tool yet added to humanity's arsenal against climate change. For the scientists themselves, the moment was emotional. Some had devoted entire careers to fusion without ever seeing more than fleeting bursts of stability. Younger researchers described the 22-minute burn as watching the future flicker to life in real time. The sight of steady plasma glowing in the confinement chamber became a symbol of persistence, a reminder that decades of setbacks could yield sudden leaps forward. While the October achievement captured headlines, the questions it raised were even larger. Would governments maintain momentum and fund the next generation of reactors? Would private companies, already racing to commercialize compact fusion systems, outpace state-backed laboratories? And most crucially, could society adapt quickly enough to seize the opportunity rather than squander it through hesitation? If the power of the stars can be harnessed on Earth, then what might happen when humanity decides to aim that power beyond our planet's atmosphere? Stay with us as the untold details rise to light. China's carbon curve breaks. When China's National Bureau of Statistics released its 2025 energy report, one graph stunned global analysts. For the first time in modern history, the nation's carbon emissions had peaked and begun to decline. The curve that had risen relentlessly for 4 decades had bent downward, signaling that the world's largest emitter was finally moving past its era of unchecked growth. For climate watchers, the report was a thunderclap across the international stage. The decline did not emerge from a single policy, but from a mosaic of shifts. Industrial restructuring had already begun years earlier, as Beijing moved away from heavy steel and cement production toward high-tech manufacturing. In 2025, however, this trend accelerated dramatically. Factories once powered by coal-fired electricity increasingly ran on renewable grids, and entire industrial parks transitioned to all-electric operations in record time. Energy statistics revealed a staggering pivot. For the first time, renewables supplied more than 45% of China's electricity, with solar alone surpassing the capacity of coal in several provinces. Massive investments in offshore wind, desert solar farms, and ultra-high voltage transmission lines stitched together a grid capable of moving clean power thousands of kilometers across the country. This infrastructure feat was unmatched by any other nation. Transportation also played a decisive role. China's electric vehicle boom had long been visible in global markets, but 2025 marked the tipping point at home. Nearly 60% of all new cars sold were electric, supported by an enormous network of fast-charging stations that stretched even into rural areas. Freight transport, once dominated by diesel trucks, shifted toward electrified rail corridors and experimental hydrogen-powered fleets. Policy teeth reinforced the momentum. Provincial governments faced binding quotas for carbon intensity reductions, and non-compliant officials risked career setbacks. In a political culture where advancement depends on meeting state targets, this created a powerful incentive for local leaders to enforce emissions controls aggressively. The central government paired this with massive subsidies for clean technologies, ensuring that decarbonisation became not only mandatory but profitable. The international implications were immediate. For years, global climate negotiations had faltered on the argument that China's emissions growth nullified Western reductions. With China's curve now bending downward, that excuse evaporated. Suddenly, the prospect of holding global warming below 2 degrees Celsius seemed more attainable, provided other major economies followed suit. Diplomats framed the shift as a Paris Agreement moment reborn, one that could renew cooperation after years of stalemate. Analysts highlighted that China's green transition served dual purposes: environmental improvement and strategic economic advantage. By controlling solar, wind, and battery supply chains, China positioned its industries to profit from the global shift toward decarbonisation. Falling emissions coincided with a boom in exports of clean energy technologies, including solar panels and electric buses. What appeared as environmental altruism to outsiders was, in fact, a calculated effort to secure economic dominance in the emerging post-carbon world. Skeptics, however, cautioned against over-celebration. Much of the decline came from curbing the dirtiest industries, but China still relied on a massive coal fleet for baseline power. Some plants were running fewer hours but had not yet shut down. Others worried about the reliability of official statistics, given the history of regional governments inflating compliance numbers. Independent satellite data, though, largely confirmed the downward trend, lending credibility to the historic milestone. Public health added another dimension to the story. In cities like Beijing and Chengdu, residents noticed visibly clearer skies. Respiratory hospitalizations dropped, and local governments reported declining healthcare costs related to pollution. The improvement in air quality delivered immediate political benefits, reinforcing public support for the transition. For millions of urban Chinese, the carbon curve breaking was not an abstract climate milestone but a tangible breath of fresh air. Behind the numbers, technology quietly drove the green transformation. Artificial intelligence optimized grid operations, predicting demand surges and rerouting electricity in real time. Smart meters in homes automatically adjusted to consumption, smoothing peaks and minimizing waste. Carbon tracking platforms linked directly to government databases enabled near-instant monitoring of emissions, providing a level of oversight that would have been unimaginable just 10 years ago. For rural communities, the transformation was double-edged. Solar farms created new income streams for villages leasing land, and electrified agriculture reduced dependence on expensive diesel. Yet some areas saw displacement, as sprawling renewable projects consumed farmland. Managing the social consequences of the green transition became an urgent priority for Beijing, aware that unrest in rural areas could undermine its carefully cultivated progress. Globally, reactions ranged from admiration to unease. Western nations applauded the emissions decline but worried about China's technological dominance. Oil exporting countries watched nervously as Chinese demand for imported crude began to taper. Developing nations, meanwhile, studied China's model closely, hoping to replicate the rapid transition with their own domestic resources. The shift altered the balance of climate leadership, with Beijing positioning itself as both pioneer and supplier. The symbolic impact of the curve breaking could not be overstated. For decades, climate advocates had warned that without China, the world's battle against carbon was doomed. With the tide now turning, hopes surged that runaway emissions could be slowed. Yet the milestone also underscored the urgency of speed. Every year mattered, and the curve's bend, while historic, was only the beginning of the monumental task ahead. As researchers passed the data, one lingering question emerged. If China could bend its carbon trajectory, which nation would next find itself forced to confront the same reckoning, and how would the balance of power shift when the race to zero reached its climax? Stay with us, because the biggest revelation is still ahead. Resurrection of the giant birds. When scientists first whispered that the elephant bird might walk again, the world dismissed it as science fiction. By 2025, the whispers had turned into carefully peer-reviewed publications. Using fragments of ancient DNA extracted from eggshells found in Madagascar and bones preserved in European museums, researchers had pieced together nearly the entire genome of the elephant bird, a creature that once towered 12 feet high and weighed more than half a ton. From the moment CRISPR-Cas9 was adapted for precise gene editing, biologists had dreamed of using it for de-extinction. The elephant bird became a prime candidate. Its DNA was relatively well preserved, and it had close living relatives, the ostrich, emu and cassowary, that could serve as surrogates. With painstaking effort, scientists began inserting elephant bird DNA sequences into ostrich stem cells, effectively resurrecting traits long absent from the natural world. The project was not merely a technical feat, but a moral lightning rod. Advocates of de-extinction argued that humanity had an obligation to reverse some of the damage it had caused. The elephant bird, after all, had been hunted into extinction by humans around 1,000 years ago. Returning it to Madagascar, they argued, could help restore broken ecosystems. Large fruit-bearing trees that once relied on the giant bird for seed dispersal had struggled ever since. The reintroduction of the elephant bird might revive those ancient relationships, but opponents countered with warnings of unintended consequences. The Madagascar of the 21st century was not the same island the elephant birds once roamed. Invasive species, from rats to cats, now dominated. Agricultural fields covered much of the landscape. Dropping a 12-foot-tall bird into that world, critics argued, could create chaos, destroying crops, spreading disease, or unbalancing fragile habitats. Extinction is permanent for a reason, one ecologist declared. We tamper at our peril. ethical debates quickly spiraled beyond ecology. Religious voices questioned whether resurrecting extinct creatures was a form of playing God. Some saw it as a modern Tower of Babel, a dangerous overreach into realms humanity was never meant to control. Others embraced it as a testament to human ingenuity, a way to right historical wrongs. Philosophers framed it as a test of responsibility. If humans had the power to undo extinction, should they not try? Financial motivations soon dominated the discussion. Zoos, private investors, and biotech companies envisioned massive profits through de-extinct tourism. A living elephant bird could attract millions to exhibits, creating revenue streams unparalleled in conservation history. Critics cautioned that such commercialization risked turning de-extinction into spectacle rather than genuine restoration. Even more concerning, it could encourage reckless experiments, reviving not just birds or mammoths, but predators like saber-tooths or experimental hybrids. Public imagination soared nonetheless. Artists rendered images of children walking beside elephant birds in Madagascar reserves. Novelists spun tales of a world where de-extinct species redefined human culture. In classrooms, students debated whether dinosaurs might be next, fueled by reports of researchers extracting collagen and protein fragments from ancient fossils. The elephant bird became a symbol of a threshold humanity was on the verge of crossing, the power to rewrite natural history. Practical challenges remained formidable. Surrogacy experiments required implanting edited embryos into ostrich eggs. Success rates were low, and early trials produced malformed embryos that could not survive. Scientists emphasized patience, noting that progress in developmental biology often came in frustratingly small increments. Even so, the first viable hatchling was predicted within the next decade, a timeline that galvanized both supporters and critics into louder campaigns. Meanwhile, conservationists raised a haunting question. If billions of dollars could be spent resurrecting extinct giants, why not invest the same money into protecting species still alive but endangered? Madagascar's lemurs, for example, teetered on the brink of extinction due to habitat loss. Would resurrected elephant birds become mascots that distracted from saving living creatures? Some argued that de-extinction projects risked glamorizing the past at the expense of the present. The debate over elephant birds also reignited interest in other de-extinction projects. Mammoth embryos engineered with Asian elephant DNA were already developing in labs. Pyrenean ibex clones had briefly been brought to life before dying within hours. Passenger pigeon genomes were being reconstructed piece by piece. Each project pushed the boundaries of what was biologically possible and philosophically permissible. As these debates roared, one deeper concern surfaced. Ecosystems are not frozen in time. If an elephant bird returns, it does not step into the world it left, but into a world transformed. That world will shape it, and in turn, the bird may alter the world in ways no scientist can fully predict. De-extinction, critics warned, is not resurrection, it is invention. The elephant bird of the future may be as much a human creation as a natural revival. Still, the allure remained irresistible. The thought of watching a creature taller than a basketball hoop stride across a reserve captured the human imagination in ways few scientific projects ever had. To some, the risks were worth the rewards. To others, it was a step toward ecological arrogance. And so the elephant bird hovered at the boundary of possibility, its DNA whispering from ancient bones, its future perched between wonder and disaster. If wings that vanished centuries ago can rise again, what happens when the stars themselves whisper secrets too vast to ignore? Stay with us as the mystery deepens. The hidden anomalies of 3I Atlas. From the moment astronomers began charting the details of 3I Atlas, the object refused to play by the rules. At first, each anomaly seemed like an isolated curiosity, a number out of place here, a measurement that didn't align there. But as the list grew longer, something startling became clear. The anomalies weren't scattered oddities. They formed a pattern so consistent that the idea of Atlas as a natural object became harder and harder to defend. The first puzzle lay in its mass anomaly. Based on brightness, Atlas should have weighed only a fraction of what orbital models suggested. Its reflected light implied a relatively small nucleus, yet its gravitational influence on dust and coma behavior indicated something far denser. When astrophysicists ran the numbers, The discrepancy reached billions of tons. It was as if Atlas carried hidden ballast, mass concealed without explanation. The chemistry anomaly compounded the problem. Spectroscopic readings revealed a startling abundance of nickel without the expected traces of iron. In known stellar processes, nickel and iron form together, inseparable siblings of cosmic nucleosynthesis. To separate them requires immense refinement, precisely the kind of metallurgical process associated with industry, not nature. Atlas's spectrum read less like a cometary body and more like the scrapings of a foundry. Trajectory brought its own anomaly. Unlike Oumuamua or Borisov, Atlas's path was not random but eerily aligned with the ecliptic plane. It threaded close to planetary orbits with uncanny precision, as if tracing a deliberate tour of the inner solar system. For a rock hurled from another star, the chances of such alignment were infinitesimal. And yet here it was, skating along the same flat plane where Earth and its neighbours circle the Sun. Then came the outgassing mystery. Comets normally shed gas and dust unevenly, jets firing in directions that nudge their orbits. Atlas, however, exhibited outgassing without measurable thrust. Its coma thickened and brightened, but its trajectory never wavered. That kind of behaviour demanded explanation. Either its jets were impossibly balanced, or the outgassing wasn't driving motion at all. Some suggested this hinted at controlled venting rather than random sublimation. Individually, each anomaly might have been dismissed with strained natural explanations. Together, they forced uncomfortable conversations, the mass that didn't match its light, the chemistry that defied nucleosynthesis, the trajectory that looked plotted, not scattered, the outgassing that behaved like theatre, not physics. Atlas, piece by piece, began to look less like a comet and more like a riddle. Skeptics argued that nature is full of surprises. They pointed to oddball asteroids with hollow interiors, comets with unusual reflectivity, and bizarre interstellar interlopers like Oumuamua, whose cigar-like shape defied expectations. Yet even those skeptics admitted that Atlas's anomalies were piling too high. Once is an outlier, one astronomer wrote. Twice is coincidence. 5 times begins to demand a new category. Public fascination surged as the anomalies hit the press. Social media filled with theories ranging from alien probes to secret weapons tests. Conspiracy sites claimed Atlas was a disguised spacecraft, its strange chemistry the residue of propulsion systems. More cautious voices reminded the public that extraordinary claims require extraordinary evidence. But behind closed doors, even seasoned scientists admitted the coincidences were becoming uncomfortably thick. In laboratories and observatories, debates sharpened. Could hidden physics explain Atlas's quirks? Perhaps exotic processes in distant star systems forged nickel-rich materials in ways we had never seen. Maybe new models of outgassing could account for thrustless jets, but each hypothesis required stacking assumptions, layering improbabilities atop improbabilities. The simplest explanation, that Atlas was natural, was beginning to look like the least satisfying. Historians of science noted how familiar this tension felt. Again and again, discoveries had forced paradigm shifts only after anomalies reached critical mass. The orbit of Mercury once defied Newton, until Einstein's relativity explained it. Quasars seemed impossible until the physics of black holes was accepted. Atlas might be the next anomaly demanding a leap, one that redefined what humanity considered possible. The psychological weight of the anomalies was not lost on observers. To dismiss them as quirks preserved comfort but risked missing a transformative discovery. To accept them at face value meant opening the door to the unsettling possibility of intention that some intelligence somewhere had set Atlas on its path. Both options carried unease. Scientists found themselves caught between fear of ridicule and fear of ignoring a truth too large to overlook. As October 3rd approached, the day when multiple orbiters and telescopes would converge their gaze on Atlas, anticipation built. Would close imaging reveal a dusty, tumbling rock that simply happened to look strange from afar? Or would it show something wholly unexpected, something that made the growing list of anomalies impossible to explain away? The deeper question lingered in every discussion. When coincidences stack so high they begin to form a tower, at what point do we stop calling them coincidences and start asking who or what designed them? Let us take you inside the untold truth. The camera trap at Mars. When planetary scientists realized that 3i Atlas would pass close enough to Mars for imaging, they understood the significance immediately. Never before had 4 active orbiters been positioned to simultaneously photograph an interstellar object. The chance alignment was a cosmic coincidence, or to some a deliberate arrangement, that created the most ambitious camera trap in the history of space exploration. Unlike telescopes on Earth, orbiters circling Mars offered unparalleled advantages. Without the blurring interference of Earth's atmosphere, their cameras could capture clarity unmatched by ground-based observatories. The Mars Reconnaissance Orbiter MRO, with its high-R ISE camera capable of resolving features smaller than a meter on the Martian surface, was tasked with aiming beyond its usual domain, the black sky itself. From China's Tianwen-1 mission came another set of eyes. Equipped with a high-resolution camera normally used for cartography of Mars's terrain, Tianwen-1 offered complementary coverage. Its different orbital angle meant that if MRO missed details due to timing, Tianwen could catch them from another perspective. Redundancy in imaging increased the odds of success in capturing Atlas's fleeting pass. Europe's ExoMars Trace Gas Orbiter joined the effort with specialized spectrometers. While it lacked the ultra-sharp cameras of its counterparts, its instruments could dissect the chemical fingerprints of Atlas's coma, breaking down gases at spectral resolutions impossible from Earth. This gave the international team a chance not only to see Atlas but to smell it across wavelengths. Older but still capable Mars Express provided the final piece. Launched in 2003, its instruments were less advanced than the others, yet its long service and stable systems made it a trusted witness. Its participation ensured that even if newer orbiters faltered, Mars Express would provide baseline confirmation of Atlas's appearance and behaviour. What made the campaign historic was the sheer coordination involved. Each orbiter moved at different speeds around Mars, with unique orbital inclinations and timing windows. Mission planners worked for months to choreograph the moment, adjusting spacecraft attitudes and schedules to ensure that all 4 could lock eyes on Atlas during its brief approach. It was like positioning 4 cameras across a vast stadium, all set to capture the same runner sprinting past. The technical challenge was immense. At closest approach, Atlas would still be tens of millions of kilometers from Mars, appearing as little more than a faint smudge against starfields. To isolate it, teams used predictive models refined daily with Earth-based telescope updates. Commands were uploaded to orbiters hours in advance, leaving no margin for human correction once the sequence began. Success depended entirely on precise mathematics and the flawless execution of automated systems. Scientists knew that if the imaging succeeded, the rewards could be extraordinary. HiRISE alone could achieve 30 km per pixel resolution at the distance Atlas would pass. While this might not reveal surface structures in detail, it was enough to distinguish between a massive cometary nucleus and a small object cloaked in dust. The difference would shape whether Atlas could plausibly be natural or not. The camera trap was also symbolic. For decades, Mars had served as humanity's lookout point, with orbiters circling tirelessly, collecting terabytes of data on geology, climate, and potential habitability. Now, those same orbiters were being repurposed as interstellar sentinels, turning outward instead of inward, scanning for truths beyond their original mission. In this moment, Mars itself became a platform for cosmic investigation. Public engagement surged as news of the effort leaked. Space enthusiasts began referring to the campaign as the Atlas Stakeout. Social media filled with speculation about what the images might show. Some joked about blurry photos sparking more questions than answers. Others, more serious, suggested that the coordination of 4 separate space agencies to focus on one target was itself unprecedented, a quiet rehearsal for the kind of cooperation required if humanity ever confirmed extraterrestrial technology. Beyond the technical and symbolic lay a deeper implication. If Atlas truly behaved as no natural comet should, then capturing simultaneous images from multiple instruments would remove doubt. In science, redundancy is power. 4 orbiters documenting the same object would strip away accusations of error, bias, or misinterpretation. The data, once acquired, would be nearly unassailable. Among the scientific community, anticipation built to a fever pitch. Would the images reveal a bulky nucleus consistent with ice and rock, confirming Atlas as merely unusual but natural? Or would they instead show a faint, compact object hidden within a vast, unnatural coma? Too small to explain its mass, too engineered in appearance to dismiss. Either outcome promised to be historic, reshaping our understanding of what drifts between the stars. In the weeks leading up to the pass, tension mounted as one by one the orbiters ran their calibration tests. Instruments warmed, software patches uploaded, orientation systems checked. Mission planners understood they were gambling on a one-time shot. Once Atlas slingshotted past Mars and continued its escape trajectory, the opportunity would vanish forever. There would be no second chance. The night of the observation became something of a global vigil. Across continents, research teams stayed awake through the hours, waiting for the signals to confirm whether the orbiter cameras had locked on target. The data would take time to downlink, but the world already held its breath, aware that images taken on that night might answer one of the most profound questions of modern science. And as the silence of deep space carried those frames back toward Earth, one haunting thought settled over the watchers. What if, when 4 orbiters stared at the same ghost, they captured not silence but a signal? Stay with us to uncover the details. The chemistry of the impossible. When the first spectral readings of 3i Atlas arrived at observatories, researchers expected the familiar: traces of carbon, silicates, frozen volatiles like water and carbon dioxide. Instead, the data struck like a thunderclap. Nickel appeared in abundance, but iron, its inseparable twin in known cosmic chemistry, was conspicuously absent. The observation shook astrophysicists because nature does not forge nickel without iron. The universe, it seemed, had skipped a rule. Spectroscopy has long been the astronomer's scalpel, slicing starlight into bands that reveal hidden elements. In Atlas's spectrum, the nickel lines blazed with unusual intensity, while iron's characteristic signatures vanished. To grasp the oddity, one must understand stellar furnaces. In supernova explosions, iron and nickel are forged together as end products of nuclear burning. No natural pathway produces one without the other. For Atlas to display this separation demanded an explanation that bordered on the impossible. Theories flooded in. Some suggested that Atlas might be the remnant of a long-vanished planet, its core somehow stripped of iron but enriched with nickel. Others argued that bizarre magnetic fields in its birthplace could have preferentially concentrated one element. But such models strained credulity. Each hypothesis required highly specific conditions unlikely to occur once in a universe, much less within reach of human instruments. Comparisons to human metallurgy became unavoidable. On Earth, nickel-rich alloys are deliberately refined for aerospace applications, prized for their durability under extreme heat. The resemblance of Atlas's spectral lines to such alloys unsettled scientists. Could the object's chemistry resemble engineered material rather than natural ore? The idea was dismissed in official publications as premature speculation, yet it lingered in conversations, whispered at conferences, and hinted at in cautious footnotes. The anomaly grew sharper with subsequent measurements. Observatories using different instruments, from Chile's Atacama Desert to Hawaii's Keck Observatory, confirmed the strange readings. Independent verification removed the possibility of error. It was not a calibration glitch or atmospheric distortion. Atlas truly carried nickel without iron, an elemental divorce unknown in astrophysical literature. Planetary scientists attempted another angle. Could unusual outgassing be hiding iron signals? Perhaps iron particles were locked in dust too coarse for detection. Yet modelling showed that even in such scenarios, iron lines should still bleed faintly into the spectrum. Their absence was too stark, too absolute. The chemistry was not just odd, it was unprecedented. The discovery sparked renewed interest in exoplanetary geology. If Atlas represented material from an exotic planetary body, it might hint at worlds with chemistries vastly different from Earth's. Imagine planets where nickel dominated geology, shaping landscapes alien to our imagination. But again, skeptics pointed out that even in distant systems, physics must obey universal rules. The problem was not lack of imagination, it was that the data itself refused to fit the template. Public fascination latched onto the idea of engineered chemistry. Documentaries speculated that Atlas might be debris from an ancient craft or a fragment of extraterrestrial industry. Science fiction writers wasted no time weaving narratives where civilizations seeded the cosmos with alloyed messengers. For the scientific establishment, this attention was both blessing and curse. It drew eyes to their work but risked associating serious research with unfounded sensationalism. Inside laboratories, chemists studied analogues of Atlas's spectrum against known industrial alloys. The similarities were uncanny. Nickel-rich compositions used in turbines and jet engines matched Atlas's signatures more closely than any natural meteorite ever catalogued. This did not prove artificiality, but the coincidence was unsettling. The object in the sky mirrored the very materials humans forged for endurance against heat and stress. The implications extended beyond curiosity. If Atlas was truly composed of refined nickel without iron, its density and structure would differ radically from comets or asteroids. Models suggested a metallic toughness that could survive deep space journeys without fragmenting. Its stability, combined with its anomalous chemistry, made some scientists privately wonder whether they were observing not just a rock, but an artifact. Cultural echoes surfaced quickly. Just as the discovery of pulsars in the 1960s had briefly been nicknamed LGM for Little Green Men, so too did Atlas's spectrum earn nicknames among graduate students: Nickel's Gift and the Foundry Ghost. These jokes masked deeper unease. When jokes circle around the same implication, they reveal what cannot yet be said aloud. The controversy spilled into peer-reviewed journals. Some authors insisted on framing the anomaly as natural but rare, invoking scenarios of hypernova ejecta or exotic stellar nucleosynthesis. Others urged restraint, arguing that until Atlas was studied up close, speculation was dangerous. Yet beneath the cautious language, one fact remained undisputed. The chemistry made no sense within the boundaries of known astrophysics. Perhaps the most haunting aspect was not what Atlas contained, but what it lacked. In science, absence is often as telling as presence. The missing iron lines were an absence that screamed louder than data ever could. Something about Atlas defied the cosmic rulebook, leaving scientists staring at spectra as though they were coded messages from another intelligence, or from a universe stranger than imagined. As debates raged, one realization grew inescapable. Chemistry, the most universal of sciences, was no longer safe from shock. If even the periodic table's order could be bent in the cold dark of interstellar space, what other certainties might collapse when Atlas revealed its full face? Come along as we uncover the hidden story and all. The weight of the universe. When astronomers calculated the estimated mass of 3 Atlas, the figure that emerged was staggering. Roughly 33 billion tons, equivalent to a small mountain carried through interstellar space, yet its visible dimensions, even allowing for a vast coma of dust and gas, did not reconcile with such weight. This mismatch became one of the most troubling anomalies. How could something so heavy wear the disguise of something so insubstantial? Mass in astronomy is never guessed lightly. Scientists infer it from multiple clues: the way dust behaves around an object, the speed at which material jets outward, and the orbital tug it exerts on surrounding particles. For Atlas, all signs pointed to a bulk far greater than its faint glow suggested. It was like watching a ghost cast the shadow of a giant. The problem deepened when compared with known comets. Even the largest comets in our solar system, like Hale-Bopp or Bernard-Danieli-Bernstein, carried nowhere near Atlas's implied mass relative to their brightness. The ratio was wildly out of scale. For Atlas to be natural, it would require a composition denser than any cometary material ever recorded. Something within its body was holding extraordinary weight in a frame that appeared too small. Ideas emerged that Atlas might contain a core of solid metal, a fragment of planetary crust or mantle blasted into space by ancient cataclysms. But the density estimates exceeded even iron-rich asteroids. If such cores were common, astronomers reasoned they should have been spotted before. Instead, Atlas seemed alone, a singular heavyweight drifting among lightweight wanderers. The statistical odds only worsened the puzzle. Based on current models, an interstellar object of Atlas's mass should pass within Earth's observational reach only once every 10,000 years. The fact that we detected it yet so soon after Oumuamua and Borisov added layers of improbability. Either humanity was inexplicably lucky, or the models themselves were flawed in ways no one had foreseen. The possibility of a hidden population of massive interstellar bodies began to surface. Perhaps the galaxy was littered with dense fragments from planetary destruction, and our instruments were just now becoming sensitive enough to notice. But if that were true, why had no previous surveys picked up even hints of such objects? Their gravitational effects should have revealed themselves long ago, in the delicate dance of stars and nebulae. A more unsettling idea gained quiet traction: that Atlas's weight was not a product of accident but of construction. If an intelligence wanted to send a messenger across the void, embedding mass would serve as insurance. Heavier objects resist perturbation, holding their course through the chaos of interstellar space. In such a scenario, Atlas was not just an anomaly but a deliberate design. Its enormous weight chosen for durability, skeptics countered with naturalistic explanations. Perhaps the dust models were flawed, or sublimation rates had been miscalculated. But with every recalibration, the numbers remained stubborn. The weight persisted, immovable, like an invisible hand pressing Atlas deeper into credibility's ledger. Each new analysis only sharpened the contradiction. Too massive for its appearance, too frequent for its odds. In the halls of observatories, whispered comparisons emerged with dark matter. Just as galaxies rotate faster than visible mass allows, Atlas too carried invisible weight. Could some exotic form of matter lurk within, something opaque to light but not to gravity? If true, Atlas might represent a rare sample of the universe's hidden scaffolding, drifting into our reach by cosmic accident. Such a discovery would rewrite physics itself. Meanwhile, philosophers and cultural commentators seized on the metaphor. The weight of the universe, both of them said, was not just literal, but symbolic. Atlas became a mirror for humanity's anxieties, unseen burdens carried quietly until numbers forced their revelation. Its invisible tons echoed our own hidden costs, ecological, political, existential, pressing down whether acknowledged or not. Engineers studying the anomaly considered its implications for travel. If Atlas truly carried density far beyond expectation, its inertia would make it nearly impossible to deflect. With such an object on a collision course with the Earth, humanity's defensive technologies would be useless. The thought unsettled planetary defense specialists, who realized Atlas might represent not just a mystery, but a hazard class beyond their planning. The media seized on these fears. Headlines painted Atlas as the impossible mountain in the sky. Documentaries dramatized its hidden bulk with graphics of ghostly titans drifting silently among stars. Public fascination grew, not because people understood the math, but because the contradiction was so intuitive. Something that looked small yet weighed colossal tons was inherently unnerving. For scientists, the pressure mounted. To dismiss Atlas as a statistical fluke risked appearing blind to data. To suggest deliberate design risked reputational ruin. Between those poles lay a narrow path of cautious language, phrases like anomalous density and unexplained mass-to-luminosity ratio. Yet no careful phrasing could erase the simple truth. Atlas weighed more than it had any right to. As the object moved deeper into the solar system, astronomers watched with intensity, hoping fresh observations might clarify the riddle. But every new measurement only tightened the paradox. The weight was real, the disguise remained, and the odds that it was natural shrank with each recalculation. What else lies hidden in the cosmos, masquerading in plain sight, carrying masses that defy our expectations until they pass too close to ignore? Come with us to know the probability collapse. When Avi Loeb compared the odds of encountering Atlas to winning the lottery on the first ticket, he wasn't exaggerating. The numbers refused to add up. By every established model of interstellar debris, the odds of detecting such an object within a human lifetime were vanishingly small. Yet here it was, the third interstellar visitor detected in less than a decade. The improbable was happening too often to remain improbable. Probability is the quiet backbone of astronomy. It guides expectations, shapes surveys, and frames discoveries within a logical scale. For decades, models predicted that interstellar wanderers like Oumuamua would appear once every few centuries at best. Instead, reality delivered a rapid-fire sequence. Borisov, Atlas, and others now whispered to be on the horizon. The framework bent until it snapped, leaving statisticians scrambling to explain why the universe seemed suddenly crowded. Astrophysicists revisited their assumptions. Maybe interstellar objects were always common, and only now were telescopes sensitive enough to notice. Yet the density required to explain 3 detections in such short order exceeded theoretical limits by orders of magnitude. To match the data, the galaxy would need to be swarming with rogue bodies, each flung from its home star in numbers beyond comprehension. The cosmos, once thought sparsely populated with travelers, suddenly resembled a traffic jam. Mathematicians coined the phrase probability collapse to describe the situation. Like a bridge straining under weight, the statistical models had buckled, no longer capable of carrying the observations they were meant to explain. Collapse didn't mean error alone. It meant a failure so deep that a new framework was required. What once seemed reliable calculations now looked like scaffolding around a building that had already fallen. Some argued that human perception itself was the culprit. Probability, after all, is only as good as the assumptions it rests upon. If the assumptions about how stars eject material were flawed, then the calculations would crumble. Perhaps planetary systems routinely hurl massive debris into space during early formation stages, filling the galaxy with more wanderers than anyone imagined. But even this explanation strained to account for the scale required. Others turned toward intention. If Atlas's chemistry, trajectory, and mass were already strange, then the statistical anomaly added a final layer. What if we were not looking at accidents of nature but placements? A handful of engineered objects would naturally seem to break probability, because they were never subject to random distribution in the first place. Like loaded dice, their existence would not conform to the game's rules. Historians of science pointed out that paradigm shifts often begin with probability failures. The ultraviolet catastrophe in the early 1900s forced physicists toward quantum mechanics. The unexpected orbit of Uranus led to the discovery of Neptune. Atlas's improbabilities, they suggested, might be leading us toward another revolution. The collapse of numbers might be the first crack in a larger wall of understanding. For the public, the language of statistics became a cultural metaphor. Articles described Atlas as a cosmic coin toss that keeps landing on its edge. Commentators wondered if humanity was at a historical hinge point, encountering anomalies in rapid succession because the time was ripe for discovery. The metaphor of collapse resonated with an era already marked by failing institutions and uncertain truths. The universe too seemed to be shrugging off its probabilities. Within observatories, frustration mounted. Scientists who spent careers refining models now faced data that laughed at their work. Graphs once clean and predictable now appeared jagged, out of scale. Some younger researchers embraced the chaos, arguing that astronomy was entering its most exciting period since the Copernican revolution. Older generations, more cautious, worried about leaping too quickly into conclusions that could not be retracted. The collapse also sparked introspection about humanity's place in the cosmos. If our statistical frameworks were this fragile, what else about our understanding was built on sand? The possibility that entire galactic populations had gone unnoticed until now raised unsettling questions. Were we blind, or were we being shown only what someone or something wanted us to see? Philosophers seized on this uncertainty. They argued that probability was never reality itself, only a human lens for interpreting it. Atlas's defiance of odds reminded us that the universe is not obligated to fit our equations. It is we who must adjust, reshaping our understanding each time the cosmos delivers an impossible event. The collapse, therefore, was not failure but invitation. At conferences, the debate reached fever pitch. Was Atlas part of a hidden population of heavy interstellar objects? Was it a deliberate outlier engineered to provoke our notice? Or was it a statistical fluke that simply demanded patience before patterns rebalanced? Each explanation carried consequences that rippled far beyond astronomy, touching philosophy, technology, and even geopolitics. As Atlas receded from Mars and into deeper observation campaigns, the probability collapse remained unsolved. Numbers that once promised certainty now delivered only riddles. For the first time in modern astronomy, probability had stopped functioning as a shield against the unknown, and instead became evidence of the unknown itself. If the scaffolding of statistics can no longer hold, what other foundations of science might tremble when Atlas forces the next question? Stay here as the next twist unfolds. The AI-space connection. When artificial intelligence surged into the public spotlight in the 2020s, most saw it as a human-centered story, a tale of algorithms, economics, and ethics. Few paused to consider whether our pursuit of intelligence here on Earth mirrored something cosmic, as though intelligence itself were a universal bottleneck faced by any species that reached beyond its cradle. The arrival of 3i Atlas reignited that question, forcing observers to wonder if the parallel between AI and interstellar anomalies was more than coincidence. Artificial intelligence is often described as an alignment challenge. Machines capable of creativity, decision-making, and problem-solving must be guided so their goals do not diverge dangerously from our own. Astronomers began to see a strange analogy. If intelligent civilizations elsewhere attempted to project themselves into the stars, wouldn't they face the same dilemma? How do you ensure that what you send outward, probes, constructs, or artifacts, remains aligned with the values of its creators? The comparison deepened as both fields confronted unpredictability. In AI, the risk lies in systems developing emergent behaviors that outpace human oversight. In interstellar science, the risk lies in objects like Atlas displaying anomalies that cannot be reconciled with existing models. In both cases, humanity confronts intelligence, whether silicon or stellar, that seems to slip beyond its grasp. Some philosophers propose that this was no accident. Intelligence, whether biological or artificial, might always reach a tipping point where control is tested. For civilizations beyond Earth, building probes capable of traversing interstellar distances would demand autonomy. No central control could direct a machine across thousands of years and light years. The moment such machines launched, their creators would face the same alignment challenge we now face with AI, trusting creations that could no longer be fully supervised. In the laboratories of computer science, this parallel struck a chord. Engineers working on AI safety began referencing Atlas in presentations, using it as a metaphor for unpredictability. The comet that won't fit the equations, one researcher quipped, isn't so different from the neural net that won't fit the training data. Both, they argued, demonstrated the same humbling truth. Intelligence, whether human-made or natural, creates surprises. Historians added yet another layer. They pointed out that the Industrial Revolution, the Space Age, and now the AI revolution each represented leaps where tools transcended their initial purposes. Steam engines outpaced muscle, rockets outpaced gravity, and algorithms now outpace cognition. If this sequence is universal, then perhaps civilizations everywhere climb the same ladder. Tools, machines, intelligence, and eventually, cosmic projection. The AI race and the stars we chase might be milestones on the same road. Cultural thinkers extended the analogy into storytelling. Science fiction began depicting alien civilizations not as distant biological beings, but as networks of autonomous constructs, the inevitable products of their own AI alignments. Struggles. Atlas, in this frame, was imagined not as a rock, but as a silent machine, the output of another species' trial and error with intelligence. The possibility fascinated the public, who found eerie resonance between their smartphones learning their habits and a distant probe streaking across the solar system. The practical side of the parallel also surfaced. AI promised to revolutionize astronomy itself, sifting through mountains of telescope data at speeds humans could never match. Indeed, the detection of interstellar anomalies like Atlas increasingly relied on machine learning algorithms scanning petabytes of star-field imagery. Without AI, many argued, Atlas might never have been noticed at all. The tools we fear may already be the reason we glimpse the stars more clearly. Ethicists seized on the coincidence with urgency. If AI was helping us detect objects whose existence raised questions about alien intelligence, then perhaps the timeline was not random. Humanity's encounter with artificial intelligence and possible evidence of extraterrestrial constructs might be converging for a reason. The double alignment problem emerged. We must align machines here on Earth, even as we confront the possibility that other machines, made elsewhere, are already crossing our skies. Religious voices joined the discussion in surprising ways. Some theologians suggested that the parallel between AI and cosmic probes hinted at intelligence as a universal constant, a law of creation that unfolds wherever life reaches complexity. Just as gravity shapes matter into stars, perhaps intelligence shapes civilizations into creators of autonomous agents. Seen this way, Atlas was less an anomaly and more a mirror, reflecting what humanity was becoming. Skeptics pushed back, warning against anthropocentrism. They argued that likening Atlas to AI was little more than projection, humans seeing their own obsessions written in the stars. Yet even skeptics admitted that the synchronicity was striking. Just as our species wrestled with machines that might outgrow us, we encountered cosmic anomalies that looked suspiciously like the products of machines outgrowing their makers. The debate shifted toward preparation. If intelligence everywhere converges on this bottleneck, AI on Earth, autonomous constructs in space, then understanding one, may help us anticipate the other. AI alignment research could serve as a rehearsal for how humanity might one day respond if faced with truly alien machines, built with motives we could not fathom. By taming intelligence here, perhaps we train ourselves for intelligence out there. As Atlas drifted further into the solar system, the analogy refused to fade. Each unexplained measurement reminded scientists of neural networks whose inner workings defied interpretation. Each press conference about anomalies echoed debates over AI safety. The stars and the servers seemed to whisper the same message. Intelligence is a riddle that repeats across scales, from code to cosmos. If humanity is now standing at the same crossroads faced by civilizations before us, the question becomes urgent. Will our machines remain aligned to our will, or will they, like Atlas, take trajectories we never intended? Stay with us as the secrets grow even darker. Finance in the quantum era. Millisecond dominance in financial markets has always been a game of speed. Traders with the fastest algorithms could exploit price differences across exchanges in fractions of a second. Yet in the quantum era, this advantage becomes almost unthinkable. Quantum computers can calculate probabilities and optimize trades with such speed that traditional high-frequency trading appears glacial. Financial institutions are now racing not just to compete, but simply to survive in a landscape where milliseconds decide billions. Unlike conventional computing, quantum systems manipulate qubits that exist in superposition. One qubit can represent 0 and 1 simultaneously, allowing exponentially larger datasets to be analyzed in parallel. This capability transforms financial modeling. Predicting market fluctuations, assessing risk, and arbitraging opportunities could occur in ways no human mind or even classical supercomputer can fully grasp. A portfolio that would normally require hours to simulate may now be projected in nanoseconds. Information asymmetry, long a shadow in finance, reaches unprecedented levels. If one firm gains early access to a quantum-powered trading system, it can effectively see the market before anyone else does. Traditional safeguards like disclosure regulations and auditing protocols become obsolete because the speed and complexity of transactions outpace any monitoring system. What was once considered insider trading now borders on an entirely new legal grey zone. Central banks and regulators are scrambling to respond. Quantum encrypted transactions could render conventional oversight tools ineffective. If a single firm or nation-state leverages these capabilities unchecked, the stability of global markets could collapse almost instantly. Countries with slower adoption rates may find themselves permanently disadvantaged. Their currencies undervalued, and their industries destabilized. Ethical questions abound. Is it fair for a machine to exploit an entire economy in microseconds? Can human oversight ever keep pace with quantum decisions? Economists worry that the very principles of free markets, competition, transparency, and equilibrium may no longer apply. Wealth concentration could accelerate, creating unprecedented divides between the quantum-empowered elite and the rest of the population. In practice, quantum arbitrage is already being tested in controlled environments. Experiments show that a single quantum computation could identify arbitrage opportunities across dozens of markets simultaneously. If scaled, this would make traditional hedge funds and trading floors almost irrelevant. The implications extend beyond Wall Street. Pensions, insurance funds, and even municipal bonds could experience unprecedented volatility as quantum algorithms hunt for inefficiencies with ruthless precision. Investment strategies are evolving to meet the new reality. Portfolio managers are exploring hybrid approaches, combining classical human intuition with quantum-driven prediction. These strategies emphasize quantum risk management, where decisions are modeled probabilistically rather than deterministically. Even with these precautions, a single miscalculation in a quantum system could wipe out trillions, echoing through global economies in seconds. Insurance markets face a unique challenge. With quantum computing capable of analyzing complex variables instantly, traditional actuarial models could become obsolete. Companies must rethink premiums, coverage, and risk entirely. Entire sectors may find themselves uninsurable because no classical metric can predict outcomes accurately enough for human-managed contracts. Cybersecurity takes on a new dimension. Quantum financial systems rely on cryptographic methods that are theoretically unbreakable. Yet the same technology also threatens to render all existing digital security obsolete. Financial institutions face a paradox. Their quantum-enabled algorithms are secure from external attacks, but the moment an internal flaw is exploited, the consequences are instantaneous and catastrophic. Philosophically, finance in the quantum era challenges our conception of causality and prediction. Markets were once thought to follow patterns rooted in human behavior and macroeconomic fundamentals. Quantum-driven systems, however, may operate beyond human comprehension, uncovering correlations and opportunities that were previously invisible. What seems random today could be algorithmically orchestrated tomorrow, blurring the line between chance and design. Countries are quietly entering what some experts call the quantum arms race. Just as nations once competed in nuclear technology, they now compete to build quantum financial supremacy. Firms are partnering with governments to gain early access to infrastructure, ensuring their influence in global markets. Traditional trade alliances and treaties may become irrelevant as wealth generation accelerates in ways no conventional agreement could regulate. Sociologists and ethicists warn that a quantum financial era could reshape society itself. Concentrated wealth may drive political influence far beyond current levels. Economic shocks could happen too fast for intervention, forcing populations to experience near-instant recessions or booms. Inequality could spike dramatically, raising questions about fairness, justice, and global stability. Quantum finance may also disrupt culture. Philanthropy, charitable giving, and even consumer behavior could shift when wealth generation becomes almost instantaneous. Traditional markers of financial success, home ownership, career progression, retirement savings, might lose their meaning. Society may find itself adjusting to a world where money moves faster than people can comprehend, and consequences unfold before anyone can react. Education and preparation are essential. Financial literacy in a quantum context goes beyond understanding budgets or investing. It involves grasping probability, risk, and the unpredictable nature of algorithmic influence. Universities and private institutions are beginning to offer quantum finance programs, but the pace of technological advancement makes them almost immediately outdated. Ultimately, the question emerges: can human ethics keep pace with quantum capability? Wealth, opportunity, and risk are no longer linear. They are multidimensional, entangled, and potentially destabilizing. Regulators, economists, and technologists are all grappling with scenarios that would have seemed absurd just a decade ago. The stakes are immense, and the margin for error is vanishingly small. As the quantum era of finance accelerates, one thing is certain: the rules are no longer written in human language. Algorithms may govern outcomes, and microseconds may define fortune and ruin. In this strange new world, the line between natural market behavior and engineered dominance blurs, leaving humanity to question not just how money works, but what money means in a universe governed by the laws of quantum mechanics. Could the next financial collapse come not from human error, but from a machine that thinks faster than we ever could? Stay with us as the mystery deepens. Fusion futures. A breakthrough in fusion energy has the potential to rewrite geopolitics. Unlike fossil fuels, fusion promises nearly limitless power without the carbon footprint. However, the transition from experimental reactors to commercial-scale production is fraught with technical and economic hurdles. Achieving sustained plasma confinement, controlling instabilities, and maintaining reactor integrity are challenges that have kept fusion just beyond reach for decades. Private companies are now leading the charge. Ventures that once struggled for funding are now racing to demonstrate net positive energy output. These organizations are experimenting with alternative approaches from magnetic confinement to inertial fusion, each promising unique advantages. The speed at which these startups innovate could outpace traditional national programs, introducing unpredictability into the global energy landscape. Oil-rich nations face a precarious future. Countries whose economies rely heavily on hydrocarbon exports could see their geopolitical leverage collapse as fusion becomes viable. Petrodollars may no longer buy influence, destabilizing governments, markets, and international alliances. The sudden rebalancing of global energy power could ignite economic shocks or even political upheaval if transitions are mismanaged. Energy inequality remains a looming concern. While fusion could provide virtually unlimited electricity, the rollout may be uneven. Wealthy nations with early access may dominate global energy markets, leaving poorer regions dependent on outdated infrastructure. This disparity could exacerbate existing inequalities, making the promise of abundant energy paradoxically a source of tension rather than universal relief. Fusion's environmental impact is often understated. While free from greenhouse gas emissions, reactors produce neutron-activated materials that require careful disposal. Cities dependent on fusion power must develop entirely new regulatory frameworks to handle waste safely. Failure to do so could transform a green energy revolution into an ecological gamble, undermining public trust and investment. Innovation is reshaping urban planning. Fusion-enabled megacities could rely on cheap, high-density electricity to power transportation, vertical farms and desalination plants. Regions previously limited by energy scarcity might suddenly support booming populations, yet the rapid expansion of energy availability could also strain local ecosystems, water supplies and infrastructure if development outpaces careful planning. Economic ripple effects are unprecedented. Energy costs are a foundational element of nearly every industry. As fusion reduces costs dramatically, industries such as manufacturing, transportation, and computing could experience rapid acceleration. Traditional energy markets, including coal, natural gas, and nuclear fission, may collapse, forcing a massive shift in employment, investment, and global trade patterns. National security strategies are evolving alongside energy strategies. Militaries may reconsider reliance on petroleum logistics if fusion power becomes transportable and decentralized. Energy independence could reduce incentives for territorial conflicts over resources. Paradoxically, early access to fusion technology may create new forms of competition and espionage, as nations race to secure technological dominance rather than physical fuel reserves. Research collaboration is both accelerating and fragmenting. International consortia, such as ITER, have long been symbols of cooperative science, but commercial interests increasingly dominate. Companies and nations race independently, sometimes duplicating efforts, sometimes withholding critical discoveries for competitive advantage. The tension between open science and private gain may define whether fusion becomes a shared global asset or a tool for concentrated power. The timing of fusion commercialization matters greatly. Even after scientific viability is proven, building the infrastructure to deliver energy at scale could take decades. Delays may exacerbate climate crises, leaving humanity to navigate a temporary energy shortfall, while fusion promises a future abundance. During this window, conventional energy conflicts could intensify, creating a paradox where the solution exists but cannot yet stabilize the present. Financial markets are reacting to the fusion revolution cautiously. Investments in traditional energy sectors are increasingly volatile, while fusion startups see soaring valuations. Hedge funds speculate not on production volumes, but on geopolitical outcomes, predicting which nations or corporations will emerge as energy superpowers. The fusion era, therefore, is not just a technological revolution, but an entirely new form of economic speculation. Fusion technology could also redefine human productivity. With cheap, abundant energy, automation, AI integration, and advanced manufacturing could become far more feasible. Industries that struggled under high electricity costs may suddenly scale rapidly, transforming labor markets, social hierarchies, and global supply chains in ways we cannot fully anticipate. Geopolitical alliances may realign around energy capabilities rather than ideology. Nations that pioneer fusion deployment could gain soft power influence, shaping trade agreements, climate negotiations, and regional policies. Traditional energy alliances, such as OPEC, could fragment entirely, replaced by new networks of technologically advanced countries controlling the flow of next-generation power. Energy diplomacy could take on entirely new dimensions. Countries with limited natural resources may pursue partnerships or technology transfers with fusion leaders to secure energy access. Negotiations may hinge less on traditional commodities and more on intellectual property, reactor designs, and grid integration capabilities, fundamentally redefining the stakes of international relations. Public perception is a wild card. Fusion promises abundance, yet society may react unpredictably to its rollout. Communities near early reactors may resist due to fears of radiation, secrecy, or ecological disruption. Conversely, access to cheap energy may trigger social unrest in areas where inequities persist. As expectations rise faster than delivery, Energy politics, therefore, is not merely about technology, but the management of human expectations. The environmental balance is subtle. While fusion reduces carbon emissions, mass adoption could drive resource extraction for reactor materials like lithium, rare earths, or tungsten. Mining practices may inadvertently create ecological damage, complicating the narrative of fusion as a purely clean energy source. Sustainable supply chains must be designed in tandem with reactor deployment to avoid undermining environmental goals. Education systems must adapt quickly. Engineers, policymakers, and technicians need specialized skills in plasma physics, cryogenics, and quantum controls. Universities are expanding fusion curricula, but the pace of technological change could outstrip traditional training programs. Rapid knowledge transfer becomes essential, as the first nations to develop expertise may hold disproportionate advantage. If energy abundance arrives before society is ready, will it save us or leave the world more fractured than before? Come with us to explore the hidden corners of the story. Carbon wars. Nations are increasingly treating carbon not as a pollutant but as a geopolitical tool. Cap-and-trade systems, once intended to incentivize emission reductions, are evolving into instruments of influence. Countries with excess carbon credits can leverage them economically, selling access to emissions allowances to industrialized nations. This trade, subtle at first, has the potential to shift power in ways that rival traditional resource wars. China has emerged as a leader in carbon markets. Its rapid industrial transformation has been paired with aggressive investment in clean technology and carbon offset infrastructure. By exporting both technology and credits, China positions itself as a global regulator of emissions, able to shape international environmental policies while simultaneously profiting. The strategic advantage lies not in fossil fuels, but in controlling the tools of decarbonisation itself. Meanwhile, Western nations are scrambling to catch up. Europe's carbon trading systems, long considered a model, now face stiff competition. The United States, historically slower to implement national frameworks, risks falling behind. Governments are realising that emissions reductions are not merely environmental imperatives, they are levers of economic influence, trade negotiation, and diplomatic weight. Carbon tariffs are emerging as an aggressive policy tool. Nations can impose fees on imported goods based on their carbon intensity, effectively penalising countries with lax environmental standards. These measures not only incentivise cleaner production abroad, but also introduce a new dimension to trade disputes. Economies dependent on high-emission industries may find themselves at a disadvantage, forced to reform or lose access to key markets. Military implications are subtle but significant. Energy transitions, including carbon regulation, can affect supply chains for critical materials like steel, aluminum, and rare earths. Nations that control low-carbon production technologies gain indirect strategic advantage. In a future conflict, carbon-efficient economies may sustain production, while high-emission competitors struggle under regulatory or trade pressures. Finance intersects with carbon politics in unexpected ways. Investment funds are increasingly linked to carbon metrics. Companies with poor emissions performance face capital withdrawal, while those advancing carbon-neutral technologies attract unprecedented funding. This financial pressure reshapes industrial priorities, sometimes more quickly than direct government intervention could achieve. Innovation in carbon capture is becoming a competitive battleground. Nations are investing heavily in direct air capture, bioenergy with carbon capture, and mineralization techniques. The ability to remove carbon at scale transforms national leverage. Countries that succeed in these technologies can offset emissions domestically and internationally, gaining both moral authority and economic flexibility. Energy inequality interacts with carbon policies. Countries rich in renewable resources may monetize their natural advantages, exporting low-carbon electricity or credits. Meanwhile, nations lacking sunlight, wind, or hydro potential may struggle to compete, deepening global disparities. The paradox of the carbon economy is that environmental virtue itself becomes a form of currency. Public perception of carbon wars can shape international relations. Populations increasingly expect governments to act decisively on climate issues. Nations that fail to reduce emissions may face domestic unrest, social movements, and political instability. Meanwhile, those seen as leaders in carbon management can wield soft power, influencing alliances, aid programs, and global summits. Legal frameworks are rapidly evolving. Carbon accounting, emissions verification, and international trade regulations are increasingly intertwined. Disputes over accuracy, fraud, and manipulation can escalate into diplomatic crises. As nations assert their rights to monitor and enforce emissions reductions abroad, environmental oversight becomes a proxy for sovereignty and authority. Technology espionage is on the rise. Advanced carbon management technologies, including sensors, AI monitoring, and capture systems, are now considered critical national assets. Theft or unauthorized access could grant foreign powers an unfair advantage, fueling a new type of global tension, one that revolves around environmental mastery rather than military might. Climate alliances are shifting. Traditional coalitions based on trade or defense are being complemented, or even supplanted, by environmental pacts. Countries may form blocs around shared emission standards, renewable technology access, or carbon credit exchange agreements. The old rules of diplomacy are being rewritten by environmental imperatives and the economic weight of carbon policy. Agriculture is not immune to the conflict. Carbon-intensive farming practices face new tariffs and restrictions. Nations that adopt regenerative agriculture gain trade advantages, while those lagging face economic penalties. Food security, once a matter of climate and logistics, now intersects directly with carbon policy, creating potential flashpoints in an already volatile global market. Industrial competitiveness is under scrutiny. Heavy manufacturing sectors such as cement, steel, and chemicals are heavily impacted by carbon regulations. Nations that innovate in low-carbon production gain an edge, while laggards risk both economic and reputational damage. Carbon efficiency becomes a measure not only of environmental responsibility, but of national economic resilience. Energy transition timelines are critical. Countries that accelerate decarbonisation too quickly may destabilise domestic economies, while those that lag risk losing global influence. The delicate balance between rapid adoption and economic stability determines whether carbon policies become tools of empowerment or instruments of vulnerability. Financial speculation in carbon markets adds an unpredictable element. Traders can profit from carbon futures, offset prices, and emission rights, creating incentives to manipulate or game the system. Market volatility can ripple through industrial supply chains, indirectly influencing global diplomacy and even national stability. Social unrest is increasingly linked to carbon inequality. Urban populations facing rising energy costs, insufficient infrastructure, or delayed renewable deployment may protest against both local governments and international trade policies. Carbon wars are not fought solely in boardrooms or on global stages. They play out in cities, factories, and communities around the world. Cultural narratives are shifting. Countries successful in carbon management cultivate prestige, moral authority, and global influence. Nations struggling with emissions often face criticism, shame, or exclusion from diplomatic platforms. Environmental success, in this sense, becomes both a currency and a weapon, capable of elevating or diminishing national standing in the eyes of the world. Could humanity find itself fighting over the planet's survival even while trying to save it? Let us guide you into what no one expected. Resurrecting the past. The revival of extinct species is no longer science fiction. Advances in CRISPR and cloning technology make it possible to bring back creatures that disappeared thousands, even millions of years ago. From woolly mammoths to giant elephant birds, scientists are experimenting with reconstructing genomes from preserved DNA, attempting to recreate life forms that were once integral to Earth's ecosystems. Mammoth projects are capturing global attention. Teams are inserting mammoth genes into the embryos of modern elephants to produce hybrids that can survive in cold climates. Beyond curiosity, the goal is ecological. Reintroducing these creatures to tundra regions could restore lost vegetation patterns, help sequester carbon, and combat permafrost thaw. Yet the ethical questions are immense. Do we have the right to manipulate life on such a scale? Elephant birds, once towering giants of Madagascar, may also see a return. Their extinction reshaped island ecosystems, and reviving them could help restore balance by dispersing seeds and controlling invasive plant species. Scientists face unique challenges, such as reconstructing flightless bird genomes from fragmented DNA, but the potential ecological benefits make these efforts irresistible to conservationists. Invasive biology presents a constant danger. Even carefully managed reintroductions risk upsetting modern ecosystems. A species revived from extinction might outcompete existing animals, spread diseases, or fail to adapt entirely. Scientists must weigh the potential benefits of revival against the unpredictable consequences for environments that have evolved in their absence for centuries. The temptation to push further is strong. While mammoths and elephant birds are within reach, proposals for reviving dinosaurs or engineered hybrids spark both fascination and alarm. Ethical oversight struggles to keep pace with technological capability. Could humanity's desire to play God ultimately backfire, introducing creatures with no natural predators or ecological checks? Decision-making authority is murky. Governments, private companies, and scientific consortia often operate in separate spheres. Some nations have embraced revival projects for tourism or national prestige, while others strictly regulate genetic experimentation. The question of who decides which species return and under what conditions raises profound philosophical and legal dilemmas. Cloning techniques themselves are evolving rapidly. Somatic cell nuclear transfer, the method used to clone Dolly the sheep, has been refined to increase survival rates and genetic diversity. Combining this with artificial wombs and advanced embryo editing, scientists can potentially create entire populations of once extinct species, reducing the need for crossbreeding with modern relatives. Funding dynamics are unusual. Revival projects are costly and require long-term investment, often beyond the capacity of government agencies. Private biotech firms, venture capitalists, and philanthropic organizations are stepping in, sometimes prioritizing spectacle over ecological responsibility. This commercialization introduces conflicts of interest that could influence which species are revived and how they are released into the wild. Ecological restoration is a driving argument. Species that disappeared due to human activity may now be restored as a way to correct past harms. Mammoths, for instance, could help reverse tundra desertification, while elephant birds might restore Madagascar's soil fertility. The revival movement frames itself as environmental reparation, yet critics warn that the modern world may not resemble the one these species evolved for. Genetic diversity is a persistent challenge. Ancient DNA is often degraded or incomplete, forcing scientists to fill gaps with genes from related species. The resulting hybrids are neither fully original nor entirely modern. This raises questions about authenticity and whether these creatures are truly resurrected species or new life forms born from human design. Public fascination drives both support and scrutiny. Documentaries, viral social media campaigns, and museum exhibits generate excitement, but also skepticism. Ethical debates, sensational headlines, and cinematic portrayals influence policy decisions, public funding, and international cooperation, highlighting the interplay between perception and scientific progress. International coordination is essential. Migration patterns, habitat availability, and climate conditions do not respect borders. A revived species in one country may wander into another, raising regulatory, conservation, and diplomatic issues. Effective governance requires unprecedented global collaboration, yet political interests often conflict with ecological priorities. Biosecurity risks cannot be ignored. Revived species could carry pathogens long dormant in ancient DNA or mutate in unforeseen ways. Protocols for containment, monitoring, and intervention are critical, yet the rapid pace of revival experiments often outstrips regulatory capacity. A single misstep could have cascading consequences for both wildlife and human populations. Cultural considerations shape projects too. Some communities revere extinct animals as part of heritage, while others may see revival as a violation of nature's course. Indigenous knowledge, local customs, and spiritual beliefs intersect with scientific ambition, creating layers of ethical complexity that must be navigated carefully to avoid societal backlash. Tourism and economic opportunity influence species selection. Projects that promise iconic, photogenic creatures attract more funding and media attention. This could skew priorities, favouring charismatic animals over those with critical ecological roles. Decisions are therefore influenced by a mixture of science, spectacle, and financial incentive. Questions of philosophy quickly emerged. Bringing back species that evolution had erased challenges core beliefs about mortality, ecological equilibrium, and human responsibility. Are we truly restoring nature, or forcing an artificial vision of the past onto a world that has already progressed? Every revived organism acts as a mirror, reflecting human ambition, hubris, and the limits of ethical judgment. As science brings lost creatures back into existence, will humanity control what returns, or will nature assert its own unforeseen rules? Stay here as the next twist unfolds. Connecting the suppressed dots. Scientific progress is not always linear, and media coverage often obscures crucial discoveries. Breakthroughs in fusion energy and the detection of potential biosignatures on Mars have occasionally appeared briefly in the press before disappearing entirely. The reasons are multifaceted. Political agendas, commercial interests, or simple editorial decisions can determine which findings reach the public and which vanish into obscurity. Fusion research, despite its monumental implications, often suffers from selective attention. Press releases highlighting incremental progress may be overshadowed by sensationalized AI news or political upheavals. As a result, the public may remain unaware of advancements that could reshape energy infrastructure within decades, creating a distorted perception of scientific priorities. Mars biosignature studies provide another striking example. Observations suggesting possible microbial life were initially reported with caution, but quickly lost traction in mainstream media. Researchers struggled to secure funding and visibility, even as the findings had the potential to redefine humanity's understanding of life beyond Earth. The suppression was subtle yet effective, illustrating how complex scientific narratives can be drowned by more immediate, emotionally charged stories. Corporate influence plays a crucial role in this selective visibility. Companies with vested interests in AI, pharmaceuticals, or energy may downplay competing discoveries that threaten market share. Public awareness is not determined solely by the merit of a finding, but by the intersection of commercial strategy, media framing, and the capacity to capture audience attention. Political pressure adds another layer. Governments may actively discourage dissemination of breakthroughs that could disrupt current policies, trade agreements, or defense strategies. Sensitive discoveries such as advanced propulsion technologies or new materials may be classified or quietly deprioritized to maintain national advantage. The public remains unaware of the full scope of scientific achievement, guided instead by what authorities deem safe or convenient to release. Peer review, while foundational to scientific rigor, can also delay recognition. Findings that challenge prevailing paradigms often face extended scrutiny, skepticism, or rejection from established journals. Radical discoveries risk being labelled as fringe or controversial, and only after years, sometimes decades, do they receive acknowledgement, if at all. Meanwhile, the narrative in the public sphere moves on, leaving suppressed breakthroughs unnoticed. The role of social media is paradoxical. On one hand, platforms can amplify obscure discoveries, allowing niche communities to discuss and disseminate findings. On the other, algorithmic prioritization favors engagement over accuracy, meaning attention can be skewed towards sensational or simplified content. Complex scientific revelations are often buried beneath viral trends, memes, or polarizing debates. Funding allocation subtly shapes the visibility of science. High-profile projects attract ongoing support and media attention, while less glamorous or riskier research struggles to maintain momentum. This dynamic creates a feedback loop. Media coverage drives funding drives research activity, and research activity drives future coverage. Suppression may therefore be accidental, arising from structural biases rather than intentional concealment. Scientific egos and professional competition further complicate dissemination. Researchers may withhold data, delay publication, or emphasize only favorable aspects of a study to protect intellectual property or career prospects. In high-stakes fields such as quantum physics, space exploration, or climate modeling, the race to be first can overshadow the collective goal of informing society. The way discoveries capture attention is shaped by cultural narratives. Public interest tends to focus on dramatic tales, alien encounters, AI innovations, or medical breakthroughs. Even transformative energy technologies can appear ordinary by comparison. Media outlets, attuned to audience appeal, highlight stories that maximize engagement, often leaving essential but less sensational science overlooked. Sometimes suppression is self-imposed. Researchers and institutions exercise caution, fearing misinterpretation, panic, or political backlash. Preliminary findings are often downplayed to avoid controversy, only to be forgotten when attention shifts elsewhere. Ironically, by attempting to protect credibility, scientists may inadvertently contribute to the disappearance of their own work from public discourse. The timing of announcements is strategic. Certain discoveries are released to align with policy cycles, investor expectations, or international summits. News that does not fit these windows risks being overshadowed or quietly retracted from headlines. This temporal filtering creates gaps in public knowledge that may last years, shaping collective understanding in subtle yet profound ways. Media consolidation amplifies the effect. A handful of corporations control a large portion of global news distribution. Their editorial priorities, economic incentives, and political relationships can determine which stories gain traction and which fade. This concentration of influence magnifies the selective nature of public awareness, meaning some scientific breakthroughs effectively never reach mass audiences. Global rivalries add another layer of complexity. Breakthroughs achieved in one nation can be deliberately withheld to prevent other countries from gaining an edge. Governments and corporations often decide strategically what to share or conceal, resulting in uneven access to knowledge. As a result, the pace of scientific progress depends not only on research quality, but also on the interplay of diplomacy, commerce, and secrecy. Public trust is affected by these patterns. When breakthroughs are inconsistently reported, people may become skeptical of science itself, assuming exaggeration or misinformation. Ironically, suppression designed to maintain stability or manage complexity can erode confidence, undermining the very institutions attempting to safeguard progress. The role of intermediaries, journalists, science communicators, and institutional press offices is crucial. Their choices in framing, emphasis, and simplification influence which discoveries capture attention. Even accurate reporting can obscure nuance, leading to the perception that certain fields advance slowly or lack relevance, despite rapid behind-the-scenes developments. Is it possible for humanity to truly understand the discoveries before us when so much remains concealed, whether by design or circumstance? Come with us as the secrets grow even darker. The coincidence stack. The universe has a habit of lining things up in ways that defy simple explanation. Scientists analysing chemical reactions, orbital trajectories, and cosmic events sometimes encounter patterns so precise that probability theory struggles to account for them. When these alignments occur repeatedly, the likelihood of mere chance becomes vanishingly small, suggesting either hidden forces or fundamental laws yet to be understood. Consider chemical coincidences. Molecules sometimes form under natural conditions in ratios that perfectly support subsequent reactions. In one documented experiment, reactive compounds in a primordial simulation aligned in sequences thought statistically impossible. These molecular chains of fate hint at underlying constraints in chemistry that guide outcomes in ways classical theory cannot fully predict. Cosmic trajectories produce equally baffling patterns. In multiple star systems, orbital paths converge with striking regularity. Occasionally, minor perturbations would be expected to disrupt orbits entirely, yet they persist in perfectly balanced configurations. Astronomers speculate that such precision may indicate invisible influences or constraints within gravitational fields that challenge conventional astrophysics. Timing adds a further layer of intrigue. Rare events, such as comet appearances or meteor showers, sometimes synchronize with human observation windows, enabling discoveries that otherwise would have been missed. When multiple anomalies coincide, trajectory, chemical composition, and observation timing, the combined probability drops to levels that approach zero, raising the question of design versus randomness. Natural systems also exhibit stacked coincidences. Certain ecosystems demonstrate highly improbable interdependencies. Predator and prey cycles, flowering schedules, and migratory patterns sometimes align with environmental shifts almost flawlessly. Biologists remain divided on whether these patterns are serendipitous outcomes of evolution or signs of deeper organizing principles in nature. Human perception complicates matters further. The mind naturally seeks patterns, connecting dots across unrelated phenomena. Yet statistical analysis of large datasets reveals that some alignments cannot be dismissed as mere cognitive bias. When multiple low-probability events converge repeatedly, the stacked coincidence phenomenon becomes objectively significant, meriting deeper investigation. Historical events occasionally display similar convergence. Rare discoveries or technological breakthroughs often emerge at moments when several seemingly unrelated factors align: social context, individual expertise, funding availability, and environmental conditions. While some dismiss these as chance, historians note that the frequency and precision of such alignments are far beyond what conventional probability would suggest. Mathematics attempts to quantify these occurrences through combinatorial analysis and Bayesian probability. When anomalies are layered, chemical ratios, orbital paths, and temporal synchrony, the cumulative odds often fall below 1%. Researchers studying such stacks must consider whether they reflect hidden natural laws, unrecognized constraints, or as yet undiscovered physical principles. Quantum mechanics introduces another layer of complexity. Entangled particles demonstrate correlations across distances and timescales that classical physics cannot explain. If stacked coincidences operate similarly on macroscopic scales, the universe may be fundamentally predisposed to certain outcomes, meaning what appears as randomness could be a manifestation of deeper interwoven probabilities. Astrobiology offers further examples. Certain molecular alignments in interstellar clouds produce amino acids and organic precursors in ratios that theoretically should be astronomically rare, yet they recur across multiple star systems, implying that life's building blocks may emerge not by accident but through processes governed by hidden structural rules. Technology enables deeper detection of these coincidences. Advanced simulations, AI pattern recognition, and high-precision sensors allow scientists to detect low-probability alignments previously invisible. What once appeared as random noise may now reveal a stacked architecture of events, exposing a hidden order embedded within seemingly chaotic systems. Skeptics argue that coincidences are inevitable in a universe with vast numbers of variables. Given enough trials, even the rarest events will occur. However, when probabilities are calculated across multiple independent domains simultaneously, chemistry, physics, astronomy, the odds become inconceivably low. These cross-domain stacks push the boundaries of rational explanation. Interdisciplinary research is crucial to understanding stacked coincidences. Physicists, chemists, and biologists must collaborate to map patterns across scales. Some suggest that what appear to be independent anomalies are manifestations of a unified natural framework. Discovering such a framework could redefine fundamental science and reshape humanity's understanding of causality itself. Deep philosophical questions emerge. Whether layered coincidences arise by design, accident, or the laws of nature, they challenge our understanding of randomness, agency, and the very fabric of reality. Humanity may exist within a universe where events are intertwined far more intricately than previously imagined. Observation bias must be carefully managed. The act of measuring and recording rare events can itself influence perception, making coincidences appear more or less frequent. Researchers employ blind studies and independent verification to ensure that stacked anomalies are not artifacts of methodology, but genuinely unexpected alignments. The implications extend to predictive science. If stacked coincidences reflect underlying constraints or intentional design, understanding them could improve forecasting in fields from climate science to space exploration. Recognizing patterns previously dismissed as chance may allow humanity to anticipate phenomena that would otherwise appear random and disruptive. Might the universe be arranging events like a concealed manuscript, embedding significance in coincidences too exact to dismiss? Follow us as the untold details rise to light. The October 3rd cameras. Advances in observational technology have brought unmatched precision. On October 3rd, a network of high-resolution cameras recorded a celestial anomaly, igniting debates over whether it was a natural phenomenon or an artificial construct. Unlike typical astrophotography, the image clarity enabled scientists to study particle composition, trajectory, and luminosity almost in real time. The size of the nucleus became a crucial detail. A large, dense core would almost certainly indicate a natural comet, formed through millennia of cosmic accumulation. Yet the cameras revealed subtler features, a compact core surrounded by a dispersed dust coma, challenging conventional categorization. Observers were left questioning whether nature alone could produce such delicate precision. Multispectral imaging provided additional insights. Infrared sensors detected unusual thermal emissions, inconsistent with typical cometary activity. Certain regions of the object warmed and cooled in cycles that did not correlate with solar radiation. These anomalies prompted theories ranging from unknown physical processes to the possibility of engineered structures. Trajectory analysis added to the mystery. The object's path did not perfectly align with predictions for solar system debris. Slight but consistent deviations suggested either previously unaccounted gravitational influences or controlled navigation. Astronomers debated whether the object represented a natural irregularity or an intelligence-guided journey, a distinction with profound implications for planetary defense and space observation. Dust composition became a key focus. Laboratory spectrometers analyzing particulate samples from the comet's tail revealed rare minerals and isotopes not commonly found in the solar system. The mixture hinted at either an exotic origin or a series of high-energy cosmic processes that defy current understanding. Each sample reinforced the object's enigmatic status. Camera networks across multiple continents captured synchronized images, enabling triangulation and 3D reconstruction. This global coordination provided unprecedented spatial resolution, revealing structures within the dust coma that appeared ordered rather than random. The implications were staggering, features suggestive of symmetry and layering that could not be explained easily by natural processes. Public attention surged. News outlets ran stories depicting the anomaly as a mysterious visitor from space, while scientists issued cautious statements. The tension between media sensationalism and measured academic analysis became evident, illustrating the challenge of conveying complex cosmic phenomena to a global audience hungry for certainty. Data verification was essential. Each image underwent rigorous calibration, accounting for atmospheric distortion, lens aberration, and electronic noise. Independent labs cross-checked findings to ensure that anomalies were not artifacts. The persistence of irregular patterns across independent datasets strengthened the case that the object was extraordinary regardless of its origin. The phenomenon sparked interdisciplinary collaboration. Physicists, astronomers, and planetary scientists pooled expertise to interpret the data. Each discipline brought different expectations. Astrophysicists emphasized gravitational behavior, chemists examined particulate composition, and engineers considered artificial design. The convergence of these perspectives revealed a deeper complexity than any single approach could resolve. Historical context added perspective. Cometary observations have always challenged human understanding, from Halley's Comet to Oumuamua. Yet the October 3rd anomaly differed. The combination of clarity, trajectory deviation, and internal structure produced a case stronger than any previously recorded, forcing scientists to reconsider assumptions about the boundaries between natural and engineered celestial phenomena. Modeling simulations pushed computational limits. Supercomputers replicated the object's dynamics under both natural and artificial hypotheses. Simulations showed that replicating the observed dust patterns naturally would require a series of highly improbable events, reinforcing speculation that either unknown natural forces or deliberate engineering were at play. Ethical questions emerged regarding disclosure. Governments and space agencies faced pressure to balance transparency with security. If the object were artificial, revealing its presence prematurely could provoke global speculation, panic, or misinterpretation. Decision-makers were forced to weigh public curiosity against the need for careful evidence-based announcements. Instrumentation revealed further surprises. Ultraviolet imaging detected transient emissions from specific dust clusters, inconsistent with simple sublimation processes typical of comets. These emissions occurred in rhythmic intervals, suggesting dynamic activity that defied current astrophysical models. Researchers speculated about possible internal mechanisms, from natural jets to artificial propulsion or stabilization systems. Citizen scientists contributed unexpectedly. Amateur astronomers worldwide uploaded high-resolution images and time-lapse sequences, enhancing professional datasets. Their observations confirmed subtle features overlooked by automated systems, illustrating the power of global collaboration in a digital era where millions of eyes can act as decentralized observation platforms. Communication networks relayed massive amounts of data in near real time. The influx of imagery and spectral analysis challenged traditional data processing pipelines, prompting rapid innovation in AI-assisted detection, anomaly recognition, and visualization techniques. These tools revealed microstructures in the object that had previously been invisible, further deepening the enigma. As humanity scrutinizes every detail, one question remains: could a single frame of this anomaly reveal secrets that alter our understanding of the cosmos forever? Stay close as the layers continue to peel back. The binary outcome. Science often assumes a spectrum of possibilities, yet certain cosmic phenomena offer only binary outcomes. The October 3rd anomaly presents precisely such a case. It is either a rare natural comet or an engineered object. There is no middle ground. Unlike complex systems where probabilities can blend, this scenario forces humanity to confront a stark, uncompromising truth. Physical analysis splits along simple lines. A natural comet would imply an extraordinary but explainable event, an anomaly within known celestial mechanics. Conversely, evidence of engineering would suggest intelligent intervention on a cosmic scale. Either conclusion challenges conventional understanding. One stretches natural law, the other expands the scope of intelligence beyond Earth. Probabilistic modelling shows that natural formation is possible but highly unlikely. The object's internal structure, trajectory, and dust emissions align in patterns so precise that chance seems inadequate. Scientists must weigh the laws of physics against the raw improbability of perfectly coincidental alignment. In doing so, they confront fundamental questions about randomness and determinism in the universe. Artificial engineering carries its own implications. Detecting signs of design would imply a civilization capable of manipulating matter at astronomical scales. The technological sophistication required would dwarf any human achievement. Such a discovery would force a re-evaluation of our place in the cosmos, challenging philosophical, ethical, and scientific paradigms simultaneously. The psychological impact on humanity is profound. People are accustomed to a world with probabilistic uncertainty, but a binary cosmic answer forces an existential confrontation. Either we witness a miracle of nature, defying expectation, or evidence emerges of intelligence elsewhere, shattering anthropocentric assumptions. Public reactions could range from awe to fear, wonder to paranoia. Contingency planning for either outcome is complex. Scientists prepare simulations for natural comet behaviour, including potential collision paths, dust dispersion, and orbital decay. Meanwhile, contingency models for artificial origin must account for unknown propulsion methods, intentions, and potential interactions with Earth or human technology. Both scenarios demand vigilance and adaptability. Historical analogues offer guidance. Humanity has previously confronted binary choices: the interpretation of early radio signals, the first identification of exoplanets, or the discovery of microbial life under extreme conditions. In each case, confirmation altered scientific paradigms, social perception, and geopolitical strategies. The binary nature of the October 3rd anomaly intensifies these consequences exponentially. Ethical considerations emerge immediately. If evidence points to artificiality, should disclosure be universal or restricted to prevent panic or misuse? Governments, scientists, and international bodies face unprecedented decisions regarding transparency, preparedness, and global communication. The stakes surpass traditional policy debates, requiring foresight in both science and societal management. Observation strategies adapt to binary possibilities. Telescopes, satellites, and sensor arrays are focused not just on tracking the object, but on detecting subtle indicators of origin. Teams prioritize signatures that could differentiate natural versus engineered characteristics, including microstructural symmetry, material composition, and energy emissions. Accuracy in detection is critical. A misinterpretation could lead to catastrophic misunderstanding. Analyzing the data presents a collective challenge. Astronomers, physicists, engineers, and data scientists must combine insights quickly. Each discipline applies distinct criteria. Natural explanations depend on cosmic physics, while artificial scenarios require assessments of engineering plausibility and signs of intelligence. Coordinating these evaluations demands an unprecedented level of interdisciplinary collaboration. Time pressure amplifies stakes. The object's proximity to Earth and observable trajectory create narrow windows for meaningful observation. Every second counts. Delayed conclusions risk lost data and missed opportunities to verify characteristics. The binary nature means that decisions cannot be postponed indefinitely. The universe demands an answer, yes or no. Communication strategy becomes critical. How scientists frame preliminary findings could influence public perception and policy. Overstating certainty risks alarm, understating significance risks complacency. Media and government must balance scientific integrity with public understanding, navigating a fine line where clarity and caution are equally necessary. Simulated scenarios reveal broader consequences. If natural, humanity gains a profound lesson in cosmic mechanics and the limits of probabilistic modelling. If artificial, civilization confronts evidence of intelligence with unknown intent, prompting re-evaluation of planetary security, philosophy, and even religion. Both outcomes require humanity to adapt rapidly to new frameworks of thought. Preparing for the anomaly requires peak technological readiness, global cooperation, and clear public communication. Instruments must operate at maximum precision to detect subtle cues, while nations navigate conflicting interests and treaties to manage observation and data sharing. Education and outreach are crucial to prevent misperception or panic, as the object's nature, whether natural or artificial, carries profound implications. Humanity faces a stark binary outcome, forcing scientists, policymakers, and the public to confront extremes where every decision and interpretation carries heightened consequences. Might one revelation transform humanity's view of existence and our role in the cosmos forever? Let us take you where the story turns shocking. The dots that refuse to disconnect. The universe has a way of presenting puzzles that defy conventional explanation. Tiny inconsistencies in datasets, fleeting signals, or improbable coincidences may appear trivial at first glance, yet when examined collectively, they hint at patterns that demand attention. These refusing dots are not random. They reveal hidden connections that could illuminate the deeper workings of reality itself, suggesting the cosmos may be far more interconnected than previously imagined. Among these enigmas, Atlas, the object captured in the October 3rd cameras, stands as a reflection of humanity's relentless curiosity and ambition. Its existence, whether natural or engineered, challenges assumptions about randomness, design, and intelligence. Each anomaly it presents compels scientists to rethink foundational questions about causality, observation, and the boundaries of human knowledge, prompting new models and hypotheses that stretch both imagination and rigor. Long-forgotten discoveries regain significance when viewed alongside Atlas. Suppressed breakthroughs, from fusion energy to potential biosignatures on Mars, have often been overshadowed by politics, media cycles, or neglect. Aligning these pieces with Atlas's data uncovers a tapestry formed across decades, suggesting the cosmos may subtly orchestrate the clues it leaves behind. Each connected detail amplifies the mystery, hinting at patterns invisible until the dots are intentionally linked. The human mind adds complexity. Our instinct to seek causality drives us to weave stories from fragmented signals, yet the dots may demand a perspective beyond narrative. They may require understanding that integrates quantum mechanics, astrophysics, and ecological systems. By resisting premature conclusions, scientists confront their biases and the universe's subtlety, learning to approach anomalies with skepticism and openness. Emerging technologies illuminate patterns once invisible. AI-assisted analysis, global sensor networks, and high-resolution imaging allow anomalies to be correlated across time and space with precision. These tools reveal structures and alignments suggesting certain phenomena are far from isolated accidents, hinting at a broader cosmic system. Even minute signals, once dismissed as noise, now form part of a larger, intricate puzzle. Questions of ethics become unavoidable. If connecting these dots uncovers signs of intelligent design or a previously unseen natural order, how should humanity respond? Which discoveries should be shared, and which safeguarded? The act of interpretation carries consequences as profound as the discoveries themselves, shaping society, global policy, and the trajectory of future science. Decisions made now could define humanity's relationship with the universe for generations. Which part of 3i Atlas fascinates you the most? The improbable alignments, the mysterious internal structures, or the hidden patterns that seem almost deliberate? Share your thoughts in the comments and let us know how you interpret this cosmic puzzle.